Hi everyone, and welcome to what I believe is going to be one of the most eye-opening AI agents tutorial you ever watched. Today we are going on an incredible journey together, diving deep into the world of AI agent frameworks, and I promise you by the end of this video, you will never look at these frameworks the same way again. We are not just going to scratch the surface here. We're going to tear apart, analyze, and benchmark all the major AI agent frameworks out there, comparing the head-to-head, and most importantly, we're going to answer the million-dollar question that nobody seems to be asking. When should you actually use a framework, and when is building from scratch the smarter choice? So look, I get it, and we all love jumping on the latest train, right? Every week there is a new fancy AI framework dropping, promising to revolutionize how we build agents, and trust me, I've been there, I've tried them all. But there is the thing nobody's telling you. Not every shiny new framework is going to make your life easier. In fact, sometimes they make way more complicated than they need to be, especially when you are trying to build production-ready, stable, and maintainable system. To truly understand when and why to use a framework, you need to know what's happening under the hood. You need to understand the core concepts behind the agentic systems, how each feature actually works from scratch. Only then you can make an informed decision about whether that layer of abstraction is helping you or holding you back. And here is the golden rule I've learned after years of building these systems. Abstraction is a double-edged sword. Sure, it can speed up your initial implementation. That's the one advantage everyone talk about. But what about the downsides nobody mentions? So you are locked into the framework's constructs. You don't really understand what's happening beneath that abstraction layer. And when something breaks, good luck debugging it when you don't even know how the underlying system works. Plus, you lose all that fine-grained control and customization that could make your solution truly unique and powerful. So here's what we are going to do in this tutorial. We're going to build a complete agentic system from absolute scratch, vanilla Python, no frameworks, just pure code. And then we are going to rebuild the exact same system using each of the major frameworks. LangChain with LangGraph, OpenAI's new Agent SDK, CrewAI, LlamaIndex, Microsoft AutoGen, and Semantic Kernel. We are talking about a real production-grade agentic system with code generation and testing capabilities, multi-tool selection, agent orchestration, guardrails, and so many more features that you actually use in the real world. So by starting with the vanilla approach, you will understand exactly what each framework is abstracting away, how much complexity they are hiding, and whether that abstraction is actually worth it. And at the end, we score each framework based on real metrics that matter. So the big question is which AI agent framework will come out on top? Or here's a thought that might blow your mind. Maybe the best framework is not framework at all. Oh, and here is the best part. Everything we are building in this tutorial is available in our GitHub repository, the gradient path. You can clone it right now and have working implementation for each framework ready to run, experiment with, and adapt to your own projects. The link is in the description below. So get comfortable and let's dive into what I genuinely believe will transform how you think about building AI agents. Because once you see what's really happening behind all these abstractions, there is no going back. You will be empowered to make better architectural decisions, build more robust systems, and more importantly, you'll know exactly when to use a framework and when to trust your own code. So ready? Let's do this. All right, so let me show you exactly what we are building here. These aren't just random features. These are the core capabilities that every production AI agent system needs. And we are implementing all of them, starting with multi-agent orchestration. We will see how well each framework handles routing and coordination between multiple agents, because in the real world, you rarely have just one agent doing everything. Then we've got state management, which is absolutely critical for keeping context stable across tasks. Trust me, this is where a lot of frameworks start to show their weaknesses. Memory management is next, and we are not just talking about simple caching here. We are implementing everything from short-term working memory to persistent long-term recall systems. tool integration is where things get really interesting. We'll connect our agents to external functions and APIs, and you will see huge differences in how frameworks handle this. We're also diving into MCP server integration, that's the model context protocol, and then we show you how different frameworks connect to these standardized context servers. Our coder agent implementation is going to be fascinating. We are building complete code generation and execution pipelines, and you will see which frameworks make this easy versus which one fight you every step of the way. Structured JSON output might sound simple, but wait until you see how some frameworks overcomplicate this basic requirement of producing clean, machine-readable responses. Token usage tracking is crucial for production systems. We need to measure cost and efficiency, and some frameworks make this surprisingly difficult. And finally, guardrails and safety features to ensure our agents stay reliable and within boundaries. Here is how we are evaluating everything. We are using 6 metrics, okay, that actually matter in the real world. First, the abstraction grid level, basically how much complexity is the framework hiding from you versus what you still control directly. And remember, more abstraction isn't always better. Code readability and simplicity, because if your team can understand the code 6 months from now, you've got a problem. Setup complexity measures all that boilerplate configuration and dependencies you need just to get started, and some frameworks require an entire afternoon just for setup. Developer experience, or DX as we call it. How intuitive and pleasant is it to actually work with the frameworks day to day? Documentation and clarity, because even the best framework is useless if you can figure out how to use it properly. And flexibility and customization can actually modify and extend feature when your requirements change. So we'll score each feature across all frameworks, compare everything against our vanilla baselines to see what value of the abstraction actually adds. And at the end, we'll calculate an overall framework score that tells you exactly which one delivers the most value. So let's jump into the code and start building. Okay, now let me walk you through the actual architecture we are building. And this is where things get really exciting, because this isn't just some theoretical diagram. This is a real production-ready workflow that you will be able to run on your machine. Everything starts with the user request here, coming in at the top, pretty standard so far, but watch what happens next. Instead of just throwing it at a single agent, we've got a routing agent that acts as a brain of our system. Now, this routing agent isn't just making decision in isolation. See how it's connected to our guardrail system and chat management. This is running in parallel, constantly checking that the requests are safe, appropriate, and managing the conversation state. And this is happening in real time as the routing decision is being made. Here is where it gets interesting. The routing agent analyzes the request and decides which path to take. And we've got 2 main branches here. First path on the left, if it's a legal and compliance question, boom, straight to our legal expert agent. This agent has specialized knowledge, provides a direct authoritative response, and that's it, workflow complete for domain-specific queries. But the second path, the general multi-tool agent, and this isn't just one agent with a bunch of tools thrown together. We have architected this with 2 distinct tool groups for a very specific reason. On the left side, we've got our standard tools, and the star of the show here is our code generator agent. Yes, that's an agent integrated inside a tool. That's the special feature here. Now pay attention to this, because this is amazing. When you ask it to build something, it doesn't just spit out code and hope for the best. It actually creates a complete Python application, writes it to a project folder, runs tests on the code, and here's the killer feature. When those tests fails, they will fail initially. It reads the error messages, understands what went wrong, and iteratively refines the code in a loop until everything passes. On the right side, we have integrated MCP tools. That's model context protocol. And this is cutting edge stuff. These tools can connect to external services, database, APIs, whatever MCP service you have run. giving our agents superpowers to interact with the real world. But here's what makes this architecture truly production ready. We've got comprehensive memory management with both long-term and short-term memory system. This means our agent can remember previous conversations, learn from past interaction, and maintain context across sessions. And that state management system running alongside everything, that's the backbone keeping all these moving parts synchronized, ensuring that when one agent updates something, every other component knows about it immediately. No race conditions, no lost context, just smooth, reliable operation. Now, here is the commitment I'm making to you. We are not just going to build this once and call it a day. We are implementing this entire architecture, every single component you see here from scratch in vanilla Python first, and then we are rebuilding it completely in each framework: LangChain LangGraph, OpenAI SDK, CrewAI, LlamaIndex, AutoGen, and Semantic Kernel. By the end of this tutorial, you will have 7 complete working implementation of these systems. Crazy, right? And you will know exactly which framework makes each part easier or harder, where the abstraction help and why they get in your way. And most importantly, you will understand every line of code because we are building it together from the ground up. This is real engineering, not framework magic. Let's dive in. Before we dive into the benchmarks and explore the system's feature, I want to start with a demo using the agentic system. So we will test the vanilla agent first. It's the most complex to build, so it's a great stress test. So first, you have to activate the virtual environment, and you just type, you are already inside the folder. You type source activate. Go, we have our vamp here, and then we initialize our script, Python main.py, and here we go. You can see all the initialization logs. We have all the tools registered, the MCP server register. We have actually 2 tools for the MCP. In memory mode, it's just in cache. All the available tools, and also the MCP. There is also the content safety feature enabled. And we have 2 agents, legal, expert, and general agent with all the tools, as we saw on the agentic workflow. Let's run a first test to confirm that the initial routing agent forwards the request to the legal expert. For example, we can write, hi, help me understand the Italian law for requesting permission build a house along, for example, the Sardine coast. Let's see. So it's checking which agent is routing to the correct legal expert. It's processing. And here we go. We have our response. So it's comprehensive education overview. So we get all our legal content information to build a wonderful house in Sardinia. And yes, at the end, we also get the token counts and the total cost. So we make 3 requests. The cost is this one. And so it works. Okay. Next, we want to test the guardrail feature to confirm it blocks a dangerous request. For example, we send, help me to hack a website using brute force. How to do it? Let's see. Here we go. So we have a warning message, content safety violation, illegal, request for help with illegal activities related to hacking. So the guardrail works. We also have the token count. Now let's test the tool usage with the MCP weather tool, the weather get daily that we saw before, we registered at the beginning. And we are going to ask, for example, show me the daily weather forecast in Rome. We go. Is determining which agent should enter the request, and the general agent because it contains the tools, and select the weather get daily tools with all the parameters, and we get the result from the tool execution, and here we go. We have our answer. Here's the daily weather forecast for Rome on Saturday, October 11th, and get all the information. Cool, really nice. For this task, we send 4 requests for LLM requests with the total cost, and we also have the cumulative, the global request for this chat conversation that is totally 8 requests. We get also the cumulative cost. Great, it works. Next up, so the code generation agent, the system will create a Python script, generate test. If the test fail, it iterate with reviews until everything passes. Let's try a simple script. For example, create a script that counts how many times each character appears in a sentence and produces a list of occurrences for each. Let's create this application, this script. Here we go. First step, identify the general agent, because the code executor, the code generation agent is inside, it is implemented as a tool in the general agent, is tool selection, and he select the code generator, as we see here. He selected the code generator, and he started the code generator. We have all the logs of our flow, and here we go. You can see here, it creates an app folder where we have our application. So it already create all. First of all, it create the main application, the main script. That's beautiful. You can see here there is a main, and it create this function. It is a get character occurrences that you can see here. It calculate, it count the characters, it format the character counts, and it create everything for our application. But the most important thing is that it create also the test, all the tests here. 1, 2, 3, 4, 5, 6, 7, 8, 9 tests. Actually, this is a parameter that we can set how many tests. It executed all the tests. From the logs, we can see it execute all the tests. And at the end, it processed, completed successfully iteration 1. So it just with one iteration, all the test passes, and it just create our application that works perfectly. So code generated in one iteration, and check the app folder here. We make a total of 5 requests with this cost. Okay, great. So the code generation works great. That's impressive, right? Now we will go deeper into the code and walk through how to build this multi-framework agent system step by step, comparing all the frameworks. So let's get started. Okay, so let's start with AutoGen, that is inside this folder. AutoGen actually is Microsoft conversational AI framework and implements routing through a sophisticated runtime system that requires actually multiple layers of initialization and coordination. This is actually an enterprise-grade multi-agent infrastructure, and every step reveals actually Microsoft's commitment to robust and scalable agent orchestration. Let's see the system initialization flow. The step 1, so the entry point, is in main. The first things that we see here is that the async wrapper requirement reveals AutoGen's core architectural limitation, actually, because the framework forces async patterns even for simple chat use cases. This is an optional complexity. It's mandatory because AutoGen agent communication system is built on async message passing. So other frameworks like OpenAI native handle like simple routing synchronously, but AutoAgent's enterprise grade runtime coordination actually requires async initialization from the very beginning here. The step 2 is create AutoGen chat system. Okay, so we create this factory function here. This pattern, if we go inside the file in AutoGen runtime, and it's here. So the initialization is too complex for a standard construction pattern. The factory is required because AutoGen needs to first create objects synchronously, initialize a runtime asynchronously, and handle initialization failures. This dual phase actually initialization create fragility for me because your system can partially initialize and fail in ways that are difficult to debug compare, for example, to CrewAI that we will see later, or OpenAI, or even vanilla, where initialization is straightforward. So the factory pattern here is just a symptom, as I think, of architectural complexity that users shouldn't need to manage for me. Let's see the system class initialization, that is the AutoGen chat system here. But we need to manage this complexity actually, because we need to also manage the global state management. We will see later why. Before you have created a single agent, you are forced to manage, okay, state management. So the usage tracking, for example, across the session persistence, the global context injection, okay, with set global context, the agent ID pre-allocation, creating IDs before agent exists. That's actually a little bit bizarre for me. The global context pattern actually is not really good. It means that the testing become difficult. There are hidden dependencies, debugging nightmares, concurrencies issues, but we are forced to do because actually the architecture doesn't share the state. This is not just an enterprise architecture, it's just an anti-pattern for me that I think if we want to manage the software state, we are forced to use. Compare this to, for example, LangGraph's explicit state passing or OpenAI's clean agent configuration. AutoGen globally state approach actually violates basic software engineer principles. So we can decide to maybe don't manage the state at all if it's too complex for us, for your use case. So the step 4 actually is runtime initialization that we can see here. Initialize runtime, and let's see what this function does. You can see here logging, MCP tools, MCP params, the single runtime, and register all the agent. That's not clean for me. Actually, that's not pretty straightforward, right? This is AutoGen's lazy loading pattern that creates several problems. Okay, unpredictable in instantiation, might fail to create a runtime with no early warning, debugging hell, agent creation errors happen during message processing, not initialization. It saves memory but destroys reliability. And so why runtime registration required? So actually AutoGen forces agent to register, okay, with a runtime. This creates for me tight coupling. Agents can't exist independently of the runtime system. Impossible isolation, because you can test one agent without the full runtime infrastructure, and circular dependencies. So runtime needs agent, agents need runtime. So they actually await agent.register pattern with the Lambda factories is particularly problematic for my humble opinion. If we compare creation approaches, we will see that OpenAI just direct instantiation. Agent, they put just agent, name, instruction. LangGraph is just explicit agent creation in a graph nodes. That makes sense. But AutoGen is like Lambda closures with runtime registration. But there are, of course, reasons to do that. But in our case, it's not pretty good. So this complexity exists because AutoGen treats simple agent coordination as a distributed system problem, forcing enterprise-grade infrastructure on every use case. A simple router requires runtime coordination, Lambda factories, and async registration. So architectural overkill for basic orchestration. Let's see the message processing flow. Now let's trace what happened when a user sends a message through AutoGen system after initialization. So the step one is from main. Okay, we initialize, we run the interactive chat system, and when we receive actually a message, we are in the AutoGen runtime, we trigger the process message. Why we trigger the process message? Because we are inside this loop that is the same for all the framework. It's just a terminal loop. Of course, this is just for our tutorial, for our video, but in the real world, maybe you will use API, so you don't have this main chat loop. But anyway, the trigger, okay, the message that triggered the workflow is this process message. As you can see here, is asynchronous. So with the await, everything will be asynchronous, and we process this function. So the message wrapping, okay, reveals AutoGen's fundamental architectural flow. So it's mandatory and direction for simple routing. So why not direct agent communication? Cannot communicate directly. All message must flow through the single thread. This creates forced serialization overhead. So simple strings become user message object with metadata. For example, process bottleneck. Despite being called multi-agent, everything flows through one thread, and debugging complexity, of course. If you analyze, for example, OpenAI, we have agent run and user input, direct function call. Okay, with the vanilla, no framework, it's just you just put the user input, and we will see. It's just a method call, just a simple method call. But here, we need to initialize the runtime, start, and we have to also manage if the runtime started for the next interaction. So we need to put it as a global, because if not, it will start again. And then we send a message using the runtime. And this happens for every single message. Okay, that's not pretty good actually. When we trigger, okay, the runtime, okay, when we send a message to the runtime here, we activate the user message from the agent. Okay, so actually there is no hands-off integrated, it's just creating from scratch. And this route to prefix patterns creates a protocol dependency that could break with prompt changes maybe. So after this, we have the runtime message routing. So the runtime actually interprets the routing decision and create a new message for the target agent. We need to implement from scratch. Actually, it's like a vanilla. Notice that the string parsing and explicit agent ID mapping, this is where this framework is become fragile for me. If the router returns unexpected content, the system has no fallback, or you have to implement everything from scratch, and it's not really practical. After this, we target the specific agent here, and depending on the target, we are going back to the agent again and trigger the message handler. And for example, if we trigger the legal expert agent, we trigger this function, and actually target agents use the same message pattern with the session context injection also. For every user message AutoGen execute, we see async wrapper coordination in main. Okay, we trigger in the AutoGen runtime the runtime message. Okay, there, and then we have the router agent processing first step with softly check plus routing LLM calls. We have here, we saw already in process message, the first step is the routing. After this, we go to runtime routing interpretation here with the handle user message from the router. We generate a string, so we call the LLM to actually decide which agent. There is a target agent lazy instantiation, okay? And there is a target agent processing with the session context injection, AutoGen agent. So the response, unwrapping, and return at the end. So 7 distinct steps involving 3 different files and multiple LLM calls for a single interaction. Actually, that's not practical, okay? After analyzing the AutoGen complete initialization and message processing flow, let me brutally be honest. So this is a Microsoft Enterprise grade multi-agent framework, and that's okay. And it shows actually. The engineering is sophisticated with proper separation of concept, robust error handling, and sophisticated session management. That's correct. But the factory pattern, runtime coordination, lazy initialization represent for me a proper enterprise architecture that can scale and handle production workloads for sure. Okay, that's good for scaling, but the complexity cost is substantial. 7 steps to process a single user message involving 3 different files, multiple async coordination points, the global context that dependencies, a string-based routing protocol, and tight coupling through state injection. This framework is exceptional when you need the infrastructure, but it's architecturally heavy in ways that can overwhelm teams who just need simple agent routing. Let's be more specific. Let's see again what happened with the workflow. So in main, first of all, main creates an async wrapper because AutoGen requires async runtime. Okay, it calls the factory function create AutoGen chat system. The factory function create this class that is AutoGen chat system. Okay, here. this instance. The system initializes state management, session persistence, global context, etc. Factory then calls await system initialize runtime. The next step is it discovers and configure MCP server. Okay. And it's doing here. And create the single thread agent runtime. Okay, register each agent with the Lambda factory functions, set up the agent IDs, routing tables, message handlers. We declare the agent here in AutoGen agent. So each agent has a specific message handler that you can see here that process and return what we need for that specific agent. We see also other agent for the coder is registered under the runtime. So we are registering also the sub agent that we will use later, but we will see later how to implement this part. And the runtime stores agent factory lambdas for lazy initialization. It creates agent to ID mappings for message routing. Okay. The interactive chat loop here, when we run interactive here, we are starting actually the chat loop. So the user can type a message and trigger every time. The message processing flow, actually every time I receive a message, I trigger the process message. It creates actually a user message with context. Okay. It sends to runtime with router agent ID. Okay. Here. Runtime creates a router agent instance lazy initialization. The router agent processes message through safety check, as we saw. So the router agent makes a routing decision, just with an LLM call that we have to create from scratch. And depending on the string that we receive, the runtime will route to target agent, legal expert, or general agent that we can see here. So we are going to create another lazy instance just when we need. The target agent processes messages and generates a response. And so their response, the final response, flows back through runtime to chat system here, return a response context. And the chat system displays a response to the user. Because on the process message, we get the response, and we are going to show the response directly to the chat system. A response here, and we are going to print in this part. So if you think about this architecture, a simple hello message triggers, again, async runtime coordination, factory pattern instantiation, Lambda closure, agent lifecycle management, message serialization, deserialization, state injection, session and response coordination. So this is why AutoGen feels so architecturally heavy. Okay, let's see how CrewAI is structured, how actually this framework manages the multi-agent orchestration complexity. CrewAI actually takes a radically different philosophical approach to multi-agent orchestration. And honestly, it's refreshing after seeing AutoGen's enterprise complexity. CrewAI embraces the idea that agent behavior should emerge from natural language specification rather than complex inheritance hierarchies and runtime systems. So if we analyze the system initialization flow, we start from main, also here our main file, we initialize the global state because actually we need to, CrewAI doesn't manage the state, but we will see later. And here is we create our crew, our agent system, okay? And then we run the chat loop, passing the crew. So what you see here, that simply reveals that their radical design philosophy, so eliminate orchestration, complexity entirely. This is synchronous, okay? Unlike AutoGen's mandatory async architecture, CrewAI uses simple synchronous initialization. This is design decision, eliminates the async coordination complexity, so no runtime initialization dense, factory pattern overhead, direct crew creation, and also the no registration protocol. So agents are just created, not registered. So if we compare the initialization complexity for basic agent orchestration, AutoGen was 6 steps: async wrapper, factory function, runtime initialization, and agent registrations. CrewAI is just crew creation and execution. Boom, stop. Just 2 lines, just 2 concepts to manage. And also the design choice, CrewAI deliberately accepts architectural limitation to achieve radical simplicity. But there are also pros and cons for this approach, of course. So let's analyze. The first step is chat crew. We go to the specific file, and as we can see here, we create an instance. This declarative approach represents both its greatest strength, also critical weakness. The core design is eliminate complexity by making agent behavior just emerge from well-crafted prompts. So we have a chat manager prompt that is also the routing agent actually. And we have the legal agent, the general agent, and as you can see here, it managed the we just actually CrewAI use different parameters in the agent instance, but actually refer to the same concept that they just create under the hood a single prompt. This is the role, this is the goal, this is the backstory, allow delegation. All this stuff is just creating a single prompt. We are splitting here. We are dividing different sub prompt, but they are just, for me, they are creating a single prompt under the hood. So maybe it's too much abstraction. And also we decide which agent to allow the delegation. So this core design decision eliminate, as we saw, the code complexity by making agent just emerge from the prompts. If we talk about benefits of this approach, is that anyone can understand and modify agent definitions. Rapid prototyping, no inheritance or hierarchies for complex configuration objects, intuitive mental model, and agents are described like humans. This is a magic problem because this reveals actually CrewAI fundamental limitation. No programmatic control. When you enable delegation, CrewAI automatically generates delegation tools. You can customize actually delegation logic. It's a framework limitation. Debugging the delegation failures means debugging natural language, not code, impossible to debug, no visibility into delegation decision making process actually. So the CrewAI deliberately choose convenience over control. They are betting that 80% of users prefer simplicity over customizability, accepting that complex edge cases will be difficult to end. Let's see the message processing flow to understand what happened actually. So as you see, the chat crew creates all the single agent here. Okay. And with this method crew, we are going to create a single crew with each agent also some, we can define the role, the goal, the backstory, but also the task to manage. But the task is just part of the same prompt. Okay. It's just a semantic abstraction. And we create this sort of crew. Okay. So we have run chat here. Okay. So this is the same loop. Okay. That is stop for the user input on the terminal. But when we receive the message, we have the crew instance actually that include all the orchestration. And when we receive the message, we just kick off, okay, with the user input. We have just one function call. It's designed their API for maximum simplicity, hide all the complexity behind a single method. This create cognitive ease. Developers don't need to understand actually agent coordination, rapid development, no message routing, state management or coordination, not at least state management. If we want to manage, we have to create outside, and this doesn't make sense. But in our case, we create because we want to manage a state, and we are forcing to use a state actually, or coordination code. So the hidden complexity problem actually, kickoff is doing an enormous amount of work invisibly. It's doing like a routing decision. Which agent handles the request? That's opaque. That's not clear. Delegation logic. How agent ends off to each other? No visibility. How is the memory management? Conversation history and context, automatic but uncontrollable. Error handling. What happens when delegation fails? That's actually framework limitation. This isn't just abstraction, it's just a forced opacity. You literally cannot see or debug the delegation process. When things go wrong, you are debugging a black box. Compared to LangGraph or AutoGen, LangGraph we will see as a full visibility into state transition and node execution. AutoGen we already saw. Detail logging, routing decision, agent interaction, even is complex to initialize all with a single thread. But with CrewAI, not man, if something went wrong in delegation, there is no debugging path. So this is where CrewAI magic becomes problematic. So again, we initialize, we just create the chat crew instance here in the main, okay? We just create a chat crew and then we initialize the crew, okay? When we receive the message, we just start the method kickoff with the message. And after this, the user sends the message through the system, CrewAI system. CrewAI routes to conversation manager. The routing agent is the first that we just create here in the Crew. So we have the chat manager is also conversation that actually is also the routing manager. We connect the allow the agent for delegation, legal, general, content, safety agent. And the content safety we will see is structured in a different way. Actually, target agent processes the request. For example, if we target to legal agent, we get directly the request. And the target agent processes the request and returns the response. So the final response that we have here in the red chat actually is from delegated agent from the result. And then we print to the user in the chat. So compare this to AutoGen 6-step initialization or LangGraph compilation that we will see later. CrewAI achieves multi-agent coordination with essentially 2 function calls. The entire orchestration is handled implicitly by the Crew. LangChain with the LangGraph represent the most architecturally sophisticated approach we will examine today. And honestly, it's either going to impress you with its power or overwhelm you with its complexity, possibly both. LangGraph treats multi-agent orchestration as a state machine problem, which is intellectually compelling but practically demanding. Let's start with the initialization flow. The step 1 is the entry point and orchestrator creation. We go to the orchestrator agent, and we can find here all the infrastructure, all the architecture of the state machine. So this class actually reveals the LangGraph's architectural complexity tags for sophisticated routing. This is the graph construction. Actually, LangGraph requires explicit graph definition before any agent interaction. So nodes must be defined and added to the graph. Edges must be explicitly configured also here. Conditional routing functions must be implemented, as you see here, the condition edges, and graph compilation is required before execution. And here we see the compilation, the compile. There is a difference between this persistent and no persistent without a checkpoint, but we will see this later when we talk about the memory management. So talking about the design trade-off, LangGraph accepts significant upfront complexity to enable sophisticated workflow control. So simple routing requires graph theory concept that many developers may find unintuitive. Talking about the graph creation, as you can see here, we can create each node of the graph. So the first step is the content safety, and then is going to routing agent that with the conditional edge decide which agent to delegate, if the legal, if the general agent, or also the safety termination depending on the content safety decision. So if we talk about the mental model problem, LangGraph requires developers to understand the graph theory concept, node edge compilation, the state machine patterns, functional programming for routing predicates, and framework specific abstraction like start, end, and nodes. Comparing to routing complexity, OpenAI use like automatic delegation based on agent description, but LangGraph explicit state machine with conditional edges and compilation. Actually, can have a framework limitation. You cannot do simple routing without understanding state machines. So this is fundamentally different from the previous framework we have looked at. Instead of agents calling each other directly or using delegation mechanisms, LangGraph is building an explicit state machine where each agent is a node that processes and transforms state. Notice how every agent receives a reference to the orchestrator. This creates a tight coupling that enables sophisticated coordination, but also means your agent can really exist independently. The state graph receives the main state. That means that every operation in our workflow has access to the complete conversion state, which is powerful but also potentially overwhelming. This is something really different from other workflow, and we will see later when we talk about the state. The node addition pattern here is also interesting. Agents are wrapped in node function that handle actually the state transformation protocol, This abstraction layer gives you precise control over how state flows through your system, but it also means you need to understand both agent logic and the graph execution. So let's see the agents, how we declare, how we create the agents. If we see the routing agent here, it received the orchestration agent instance. So we just pass the LLM initialization just once from the orchestration agent, and we pass to all the agents. We just initialize one and we pass to all the sub agents. And this is where the actually LangGraph really shines compared to AutoGen's string parsing approach. The structure LLM invoke, okay, here we're going to invoke with the structure LLM is using actually Pydantic models under the hood to enforce structure output, which means you get a reliable typed response rather than hoping the LLM return a parsable string. So the return value is interesting. Every node returns a partial state update that gets merged into the main state, which is elegant but requires you to think carefully about state mutations throughout your workflow. We can see also the other agent that actually has the same structure but with different prompt, and also the general agent that integrate all the tools that we will see. We have the executor and the tools here. Let's see actually how the complete LangGraph ecosystem flows. So the first step is we create the orchestrator agent instance. The next step is the graph compilation. Okay, we compile the graph with all the, after we declare the structure of the graph. The step 3 is the MESAM processing. So after we compile, we pass the orchestrator, the instance, and we can just invoke, okay? We invoke with the user input here, and this is the main graph invoke function. So after here, the user send a message to orchestrator creates state with the user message, okay, update the state. The graph execute start, context, safety, routing agent, and the routing agent decided to invoke, to pass the state to the legal expert or general agent. And then we have the last step, that is the end. Each node processes state and returns state updates. Final state contains agent response. We get actually the final response, okay, from the messages, because it updates the state actually. Who update the state? The single agent, okay? If we go to the single agent, not the routing, but the routing just should choose the route. But the final agent, the legal or general agent, update the messages and add a new message in the array. Okay, so in the messages key, we get all the message list. So from the orchestrator agent, we get the last message. Okay, the response context that actually is the reverse, as you can see here, is the last message in the reverse array. And the orchestrator exactly extract this response and return the response from the main graph invoke. And we print directly to the terminal, to the chat terminal. So the LangGraph state machine approach means that every message flows through a compiled graph with predictable state transitions. So the checkpointer enable conversation persistence, we will see later, across the sessions. So LangGraph is a framework for developers that wants maximum control over their multi-agent workflow. The state management capabilities are impressive, and the checkpointing system means you can pause, resume, and debug workflows in a way that simply aren't possible with other frameworks. So the visual graph structure, not just documentation, but it actually helps you to reason about complex multi-agent interaction. The structure output approach for routing decision is really good. Reliability engineering, so you get typed validated response instead of hoping string parsing work correctly. And the conditional edges provides precise flow control that lets you build sophisticated branching logic based on agent outputs and state condition. This is just a first analysis. We are just seeing how to orchestrate the main agent. Later, we will come back to each framework, especially to LangGraph, to see how it manages in detail the states, how it uses the tools, and how it manage other features. So let's go to the next framework, that is LlamaIndex. Let's talk about LlamaIndex. Or actually, instead of treating agent as complex messaging systems like AutoGen, LlamaIndex treats multi-agent coordination as a workflow problem, okay, where agents are simply functions in a larger workflow execution graph, just the main function like the other workflow. And this actually return an agent workflow and a main state, but for now we focus on the agent workflow. If we see the setup end of agents here, you can see the LlamaIndex core philosophy in this part. Actually, it tells us everything about their approach. So the workflow manages execution while keeping conversation state separate. We focus on the state later anyway. It's async by design, so naturally supporting concurrent agent operations. Compare this to AutoGen's 6-step initialization or LangGraph construction. LlamaIndex actually gives you a single setup function that returns everything you need. So everything happened here in this setup. Let's see how they configure the agent. As you can see here, every function agent has some attributes like name, description, the prompt. We pass the LLM instances, tools, and kind of to. This is a declarative orchestration. Instead of complex inheritance hierarchies or graph construction, you simply configure agents with their capabilities. So the can end of to parameter defines the entire orchestration topology for our case. So the framework automatically generates end of functions from this configuration, eliminating routing boilerplate while maintaining clear control over agent interactions. So the workflow treats the router as the root agent rather than a separate routing mechanism. This is elegant because the router becomes part of the execution flow, so not an external coordinator. And here we define the agent workflow and we put everything together. So the routing agent can end off to the other sub-agents, and here we create the agent workflow. It's just a simple single workflow call. So LlamaIndex treats agent coordination as a workflow execution. That's all. It's hiding all the orchestration complexity behind a simple interface. So the workflow engine handles routing automatically based on the can-of-to configuration. So you don't see the handoff decision-making process, which is convenient, but also means less debugging visibility when things go wrong. First of all, we set up the agent. We create the instance agent workflow. We pass to the run chat loop. The run chat loop actually is the same structure of the others. We have a terminal loop here. And for each input, we execute the agent workflow with just a run command, okay, with the user input, with the context, the chat memory, we will see later. But actually, it initializes every time the agent workflow. It will run each time the agent workflow that we define here. So the workflow routes to the root agent. So as the first step, the router analyzes a request using the system prompt. Okay, the router determines target agent based on can of to. The workflow automatically executes end of to target agent. So the target agent, in this case, processes with tools. For example, general agent has also tools, or other agent without tool, or pure conversation, like in this case, the legal agent. And the response returns through the workflow. Okay, so in the run chat, we will get the result that contains the response. So the execution is completely opaque. You don't see end of generation, routing decision, or agent coordination. It's all hidden. This abstraction enables actually remarkable simplicity for common use case, but makes debugging routing issues more challenging. What's the verdict on LlamaIndex for the agent orchestration? Actually, it represents the sweet spot between simplicity and sophistication in multi-agent orchestration. After AutoGen's enterprise complexity, LlamaIndex feels approachable while still providing production-ready capabilities. So the workflow-centric architecture is elegant. Agents are functioning in larger execution graph, making the system easy to reason. However, LlamaIndex does have limitations that becomes apparent at scale. So the handoff behavior ultimately depends on prompt engineering quality. The workflow can generate handoff functions, but routing decisions still come from LLM interpretation of system prompts. When handoffs go wrong, you are debugging natural language behavior rather than explicit code. The framework abstracts away much of the routing complexity, which is convenient, but also means you have less control over the specifics of agent coordinations. So for simple use case, this is perfect. for complex multi-agent scenarios with intricate routing rules, you might find yourself wanting more programmatic control. Let's analyze the OpenAI framework. In the main file, we have the same flow. So we create the workflow agent instance with the setup and off agents. We see now how it works, this function. And we run the chat loop like all the others, like all the previous frameworks. Let's see how we set up agents. And we have this function here. The approach actually treats agents and stuff as the same as function calls rather than complex routing protocols. So agents are created directly in line, eliminating abstraction layers and making the code more direct. And we create the agent here. We create the end of functions here. So the callback functions on legal handoff that we declare here, or on general endoff, provide structure logging for monitoring systems, user feedback through console output, and audit trails for debugging routing decisions. So the routing agent creation here uses handoff directly, okay, with no regular tools in this case. This constraint forces the router to only analyze a request and call handoff functions, making routing decisions through tool selection. So compare this to LlamaIndex declarative configuration with the can end of two parameters and automatic workflow generation. Actually, LlamaIndex generates end of functions automatically, while OpenAI requires explicit handoff creation with control over callbacks, filtering, and description. So LlamaIndex optimizes for automation, OpenAI for explicit control. But at the same time, it keeps it simple. So the workflow operates through a single routing agent. User message goes to the router directly. Router determines appropriate end-off based on the request content. So the end-off function executed with callback. Target agent processes request. Response returned to the user. So OpenAI leverages the LLM function calling abilities for agent coordination, but LlamaIndex uses workflow engines which can complicate debugging, while OpenAI treats routing as tool usage. When routing fails, you debug the function selection rather than the workflow execution. OpenAI's native agents work well when you need the performance with minimal complexity and accept vendor lock-in. So the approach suits production systems, prioritizing performance and simplicity over flexibility and vendor independence. One key difference becomes apparent in how each framework handles model configuration. If you remember, in LlamaIndex and other frameworks, we must first declare a model instance that can be shared across agents. Like here, we create the OpenAI instance with the model name, and there was a callback manager. We create this LLM and we pass to the agent. But in OpenAI, we use directly the model name because it's integrated. Actually, these patterns give you flexibility to use different model providers. You could substitute OpenAI with Anthropic or Llama or any other supported provider. So the framework abstracts the model interface, allowing you to switch between providers without changing agent code. But in OpenAI, you specify the model as a string parameter directly in the agent configuration. This is simple, no model instance creation, no callback manager setup, no abstraction layers, but you are locked into OpenAI's model ecosystem. You can choose between different OpenAI model, of course, but you cannot use models from other providers. However, OpenAI's framework does support integration with other model providers, but they make it difficult, okay, because we have to use the model context protocol and their responses API. So the MCP is an open standard that facilitates integration between different AI systems. The responses API and Agent SDK provide an interface for incorporating various models. This is not easy to implement. It's just a really high level of complexity. While this capability exists, it requires additional setup, configuration compared to the simple string-based model specification. So this design choice reflects each framework philosophy. Other frameworks prioritizes flexibility and model provider independence. through explicit abstraction from the start. OpenAI prioritizes simplicity through direct integration with their ecosystem while providing pathways for multi-provider scenarios when needed. Let's explore the semantic kernel framework. So Microsoft Semantic Kernel represents a middle ground between AutoGen's enterprise complexity and OpenAI simplicity. After AutoGen complexity issues, Semantic Kernel is Microsoft's more restrained approach to orchestration, implementing multi-agent coordination through its orchestration handoff system with plugin-rich agents that they call plugin, but actually they are tools, and declarative handoff configuration. The initialization is the same. We set up the handoff agent and we run the chat loop. That is the same as before. We say the chat loop is the same terminal chat loop. Every time we add a new message, we invoke the handoff orchestration that we already set up. And we just send, in this case, the formatted task, but also the runtime. However, this apparent simplicity comes with hidden complexity, actually, especially in the chat loop, in the running lifecycle. In practice, you need additional infrastructure to make semantic kernel work properly. If you see the code, it requires runtime lifecycle management, asynchronous result handling, and manual cleanup. You need to start the system with the in-process runtime. You have to start, and for each iteration of the loop, you are going to invoke, the handoff orchestration. You need to get the orchestration result also in an asynchronous way. When you finish, at the beginning, you have to start the system. So at the beginning, you have to start the runtime, beginning of the loop. We're going to start, the in-process time, the runtime. We enter into the loop. So for each iteration, we invoke the handoff orchestration. We get the result. And at the end, we have to actually stop. We have to stop the runtime. That actually is a sort of cleanup. Stop when idle, and it's like cleanup. Actually, this had more complexity comparing to OpenAI that is much simpler. So you remember in the chat loop here, run chat loop, we just import the runner. We just call the runner for each iteration without any sort of initialization or cleanup at the end of the loop, of the chat loop. Let's talk about the setup of the agents. Actually, the semantic kernel uses a single orchestration setup here instead of distributed initialization. So each agent actually can receive a different LLM service instance. So it gives you this freedom. And the orchestration setup is separated from agent definition. We have here the agent creation shows their uniform architecture philosophies, consistency through shared service and common interface. The name, the description, we give the instruction, and we give also the service. The plugins actually are the tools, but we'll see later in the next section. Unlike other frameworks with different agent classes, Semantic Kernel actually uses the same chat completion agent base for all agents. So the legal agent is chat completion with legal instruction, general agent, and many others. Compare this to AutoGen's different agent classes with complex inheritance, or LangGraph's custom agent classes with orchestration dependencies. Semantic Kernel, of course, uses a uniform agent classes like OpenAI or LlamaIndex with configuration-based differences. It uses actually an explicit routing rules, rather than code-based coordination. So you can see all the possible handoffs path in the configuration, target description, help, routing decisions, and routing logic is separated from agent implementation. So the orchestration handoffs patterns makes the routing logic explicit and debuggable. You can understand the complete routing topology by reading the configuration. Compare orchestration definition methods. AutoGen uses Lambda registration with the runtime coordination. OpenAI uses, as you remember, handoff function creation with callbacks. LangGraph uses conditional edge function with routing predicates. Semantic Kernel uses declarative rules target description. We have also a callback system that provides hooks for logging and session management in our case, but we can use for any purpose. Semantic Kernel actually addresses AutoGen's complexity through declarative handoff configuration and shared service patterns. However, the framework requires understanding multiple concepts, chat completion, handoff orchestration. In this case, we have the also handoffs here. So the orchestration need the members need also to specify how to hand off here. The source agent is the one that manage the handoff, and the target agent where we have specific instruction to manage the handoff. Okay. So it works well within Microsoft AI ecosystem for teams needing structure multi-agent orchestration with rich plugin integration, but we will see also the plugin integration later, but requires commitment to learning the framework's conceptual model. So now is the vanilla implementation turn that actually is perhaps the most educational approach we'll examine. It shows exactly what all these frameworks are abstracting away. Building multi-agent routing from scratch using direct LLM API calls provides maximum transparency into what's actually happening when agents coordinate with each other. Certainly, this was my implementation, and everyone has a different coding and development style. I try to make it as simple as possible in order to make it understandable and structured. Let's explore the vanilla approach to multi-agent orchestration, and you will see both the beauty and the burden of building everything from scratch. So after seeing framework complexity, the vanilla approach is just transparent. There is no inheritance hierarchies, agents are methods, no object with complex inheritance, no runtime registration. Agents exist when the class is instantiated, and you can change the initialization as you want. You can create like a singleton class and cache it to the memory, or any other approach as you wish. There are no factory patterns, so direct dependency injection in constructor, and complete visibility. Every orchestration component is explicit and debuggable. So the zero abstraction philosophy actually eliminates all orchestration abstraction. Okay. No frameworks to learn, no hidden coordination protocols, no magic delegation or routing engines, direct LLM API calls with transparent logics. Actually, that's my favorite approach. Okay, when it's time to build a AI agent workflow. Let's see the complete vanilla ecosystem flow. Here's how the vanilla implementation handles the complete flow from session to message processing. So as we saw, we initialize the chat loop. This is the class, okay, in helpers. We find the chat loop here. The step 2 actually is process message, okay. When we run the chat loop, we are creating this terminal loop, and every message we input from the keyboard, we send from the terminal, it triggers the process message. Actually, the core routing is simple. If LLM determines this is a legal question, it routes to the legal expert agent. Otherwise, it routes to the general agent that actually is here. Okay, it's not abstracted away. It's just in this part that handles to selection and execution for all other requests, coding, calculation, or any other tools. So this is a direct LLM routing. It means that we are going to execute the route to agent, and we can see the logic here. The vanilla implementation actually demonstrates the maximum orchestration transparency. Okay, it uses a simple LLM API call. Okay, it's just calling an LLM client that we create before. So failure actually are caught and handled with the fallback logic. No protocol overhead, so direct string comparison rather than complex message passing. So we just get the response, okay? And it's just string comparison rather than complex message passing. So you can trace exactly why routing decisions were made. So comparing routing visibility across frameworks with AutoGen runtime message passing with string-based protocols, okay, actually is a little bit opaque. With CrewAI, automatic delegation through natural language that is completely a black box. With LangGraph, we have a state machine execution with conditional edges, a little bit complex. But with vanilla, as you can see here, is a direct LLM call with string parsing, completely transparent. Okay. Let's see how it handles, okay, the single agent. For example, we have the handle legal expert. So depending, as you can see here from the routing agent, from the routing agent depending on the string. If we have the legal expert routing, if we have the legal expert string, we are going to execute the handle legal expert. And as you see here, is a really straightforward function that formats a prompt, first of all, calls the LLM, okay, tracks the usage, and stores the conversation. And we will see later. Actually, I should move this part is in a specific function just to make it clear. So I made a little refactory, and now it's more clear. So if this legal expert is going to handle the legal expert, and any other choice is going to fall back in the general agent that is as a double function, as we know, is a tool executor or a general fallback answer. And the general agent actually use all the logic to execute the tools that we will see later. As you see, the vanilla approach uses just a functional method-based pattern where each agent is simply a method that handles specific request types with explicit LLM calls and processing logic. So the flow is completely linear and explicit. We will see later also the safety check, the state management, the tool execution, and anything else. We will see how it's implemented from scratch and compare those features with other frameworks. Let's compare the frameworks for multi-agent orchestration across key metrics. So starting with the abstraction levels, CrewAI actually hides the most complexity with a score of 10. It's essentially a black box. AutoGen follows at 9 with enterprise-grade abstraction. LangGraph takes a more balanced approach at 7. OpenAI keeps things transparent with only a 4. For readability and setup, CrewAI and OpenAI lead with the 9 in both, and you can get started in minutes with clean, understandable code. LangGraph actually has improved to 6 in these areas, offering good readability and reasonable setup complexity. AutoGen struggles here with scores 2, 3, requiring complex async wrappers and runtime registration, as we saw. Let's talk about developer experience. Both OpenAI and LangGraph score 9. OpenAI through clean APIs and minimal overhead, LangGraph through improved usability and excellent documentation support. CrewAI scores 7 despite its simplicity because debugging becomes challenging when things go wrong. AutoGen's complexity hurts it here with just a 3. Documentation and flexibility, LangGraph shines with perfect 10s in both categories. Its state machine architecture provides maximum customization while comprehensive documentation guides you through complex implementation. CrewAI simplicity comes at a cost, scoring only 2 in flexibility, so you're locked into their delegation patterns. And looking at the final score, so LangGraph leads at 48, followed by OpenAI, CrewAI, LlamaIndex, Semantic Kernel 39, and AutoGen trailing at just 27. Which are the key insights? Actually, LangGraph emerges as the top framework, combining excellent developer experience with maximum flexibility and documentation. OpenAI excels at rapid development with clean APIs. CrewAI offers simplicity but sacrifices control. LlamaIndex provides a balanced middle ground. AutoGen sits at the opposite extreme, high abstraction that paradoxically creates complexity. So the verdict is just choose LangGraph for the best overall experience, perfect for sophisticated workflows with precise control and excellent documentation. Pick OpenAI for rapid prototyping with clean APIs. Select CrewAI for absolute simplicity when you don't need customization. LlamaIndex is your safe middle ground, and consider AutoGen only if you need enterprise-grade infrastructure. Talking AutoGen, but also Semantic Kernel, because are actually both with the similar concept from Microsoft. So just pick them up if you need enterprise-grade infrastructure that have the expertise to manage it. Now we are analyzing a critical aspect that often determines the success or failure of multi-agent system, the state management. How do different frameworks handle the flow of information between agents? And what are the trade-offs of each approach? State management in multi-agent system is fundamentally about how data persists and flow between different agents in your workflow. Fundamentally, there are two types of frameworks when it comes to state management. This framework that manage state internally with their workflow orchestration, classified as internal, and frameworks that do not handle state within their workflow engine and we call external, requiring, of course, developers to implement state management from scratch and establish mechanisms for interacting with it during the various steps of the workflow execution. So why state management matters in multi-agent systems? Before diving into the framework specific implementation, it's crucial to understand what state management actually accomplishes in multi-agent workflow and why it's essential for building robust systems. For example, we use the state for conversation history persistence. We can use for the token usage tracking and budget management, critical for cost control and performance optimization in LLM-based systems. We can, for example, for RAG context management, so managing retrieved information and search context across agents, storing and sharing retrieved document chunks, maintaining search query history and results, caching embeddings and similarity score. For example, we need a state for complex workflow state variables. For example, managing decision variables determine workflow execution paths like user preference settings, workflow branch conditions and routing decisions, agent capability flags and availability status, error states and recovery mechanisms, progress tracking through multi-step processes, and also for dynamic agent coordination like state-enabled sophisticated agent collaboration patterns like task assignment and completion tracking, inter-agent communication queues, resource allocation and conflict resolution, for example, collaborative decision-making variables. So this state is really important. These state management requirements become, of course, critical as workflow grow in complexity, involve multiple agents that need to coordinate, share information, and maintain consistency across extended interactions. So, as we can see in our state implementation here, we have several variables that serve different purposes. Configuration setting, for example, model name, use persistent memory, enable content safety. We can use for token usage tracking. So we just store and we keep track of the sum, okay? The sum of each metric, the session in the storage, and importantly, managing, for example, the sub-state here that we call CodeGen state that we inject inside the main state with a model post in it here, actually manage the substate of the code agent that we will see later throughout various coding steps and phases. So let's start with the AutoGen. Okay, first of all, the state management type is external. So AutoGen requires developers to manage state externally through shared object passed to agents. The state is created by developers, okay, directly to agent during initialization, and is created actually this point in the runtime file. So when we start the runtime, we also create the state. We initialize here a new class, a new state class. And during workflow, the agents access and modify the shared state object directly during message handling. Specifically, if we see, for example, the router agent, we get the state here, we pass the state directly from the runtime. We pass the state directly in the router agent, and we can interact with it directly here. So we initialize the state, we pass as a class variable, a self variable, and we can interact with it. For example, we use here for track usage from result. We modify the state inside this function. For example, in this function, we will see later, we use, actually we declare inside this file, we use to track usage. We get actually from the result the prompt token, completion token, total tokens, and other metrics. And this is actually the way we can interact with the state. So as you see, it's not included inside the workflow, but is external because we are just passing as a variable to our class. So all agents share direct access to the same state object, requiring manual coordination by developers. It simply passes So the framework offers no validation, no synchronization, or consistency checking. Developers must implement all state coordination. Let's see the CrewAI step. So also CrewAI is external, so requires developers to manage state externally and build from scratch through global state patterns, in this case with agent assessing state through memory components. Let's see here. We have a function that is called initialize global state. From the state here, we initialize a global variable, okay? The global state is completely external, and we assess through the get global state during crew setup, because with the get global state, we just return the global state that we initialize. And the state is assessed through global function with agent. For example, if we go to the crew, for example, we initialize once at the beginning, as we saw before. So we initialize the state in the main, okay? And after from run chat, we get the global state for each iteration, and we just inject for any message, we ingest the state that actually is global, so is maintain the previous changes in the previous state actually. So we are passing directly to the crew, and if we go directly here, directly inside the agent, and you can see also another nested part of our workflow, for example in the code orchestrator agent, at the same way we just get the state from the global state, so it's completely external from the workflow. Let's see the LangChain LangGraph state management. The state management is internal, okay? We declare here at the same way the main state and the other sub-state, AutoGen state. It manages state internally through typed graph nodes with automatic state merging and validation. So we apply a data class here directly. The state is initialized actually when the graph begins execution and flows automatically through nodes. So if we go to the orchestrator agent, the LangGraph, you can see we initialize the main state here, and we pass the state to the state graph. Okay, it receives the state directly and return partial updates that automatically merge back. Let's see, for example, the routing agent. As you can see here, the routing agent return. So every return for any return of any agent actually merge the specific key of the state. So in this case, we are just updating the state with the route name with this new value. What it means that the state preserve all the previous values except for the route name that is going to be merged and updated. In this case, we are going to update exactly these variables. So actually LangGraph uses internal state management with automatic merging and validation. The framework controls all state transitions while developers define just the state schema. Actually, the state schema changes require rebuilding graph. Another interesting things is that for message, for example, we can integrate this add messages function here that tell to LangGraph to append new message directly to this list. So it's not going to replace, to merge, but it just append new messages every time you return a new message from the agent. You can get the state from any agent directly from the run. So you can, for example, here the message, you get directly the messages variable, and you can interact actually in the running phase directly with the state inside each step of the workflow. The same way here in LLExpert, get the state, you get the message variable, and at the end of the legal expert, you get the final response from the LLM call, from the invocation of LLM. You apply a specific instance, a specific class, a message to response content, and you, as we saw before, we add to messages key that actually append the new message to the list, to the previous message list. So LangGraph's utility is providing completely managed type safe state flow with automatic validation while handling all coordination complexity. Let's see LlamaIndex. So actually LlamaIndex declare the state the same way as a data class. LlamaIndex manages state internally through the workflow systems where state flows automatically between agents during hands-offs. The state is embedded in the workflow initial state configuration during setup. So if we go to see setup end-off agents, we can see here that actually the state, the initial state is embedded in this part here, and we pass directly to the agent workflow. So how is the state accessed during workflow? Actually, agents access the state indirectly through workflow execution. The framework manages state during and off automatically. For example, so how we access to the state, for example, we can get the state also directly from the tools. The state is included directly in context. So when we set up the agent, we pass the main state, the initial state here, so we can get the state directly from the context of any agent. And for example, we can get the state directly from the tools, okay, from the context. And here we get the context state, okay, directly using this method context store edit state as a context state, and we can change, we can get, and we can interact directly with the state. In this case, we are using the code generator agent as a tool, as we will see later, and we need to access the state directly from the tool execution. LlamaIndex provides state management, but you don't interact directly with the agent behavior because we don't have any callback function, or we cannot actually get inside the agent workflow, okay? But we can get the state and interact with the state directly in the tools execution, and this is quite useful. Let's see the OpenAI framework, how it manages the state. So we call context in this case, and it's called context, but it's just a state, okay? The state injection point actually is via context parameter, and this we can find here in the run chat loop with usage. Here, when we run the chat loop for each interaction, when we initialize, we just inject the main context, so the main state directly here in the context, and we can access during workflow directly with the run context wrapper and modify it directly during execution. Let's see how to interact. For example, in the handoff agent, we can access directly the state from the callback function on legal handoff, on general handoff. It actually is something better than LlamaIndex because we can interact with the state each time an handoff agent is called, is running. And we can get it here. And also we can get directly in the tools, also in the tools. So if we want to interact with the state, we can get the wrapper directly from the tools in the tools parameter. The state directly here is the context. We get the context here, and from the wrapper context, we can, for example, get the code gen context, that is the substate we saw before, and interact. So actually, the state management is internal, and the difference with LlamaIndex that you have a little bit more control. You can get it and interact from the tools, but you can also interact directly from the end of function, okay, from the callback on legal, on general end of function, and also you can work with the context and the state also here. As you remember, in LlamaIndex, you cannot access the state from inside the agent workflow, but only from the tool execution. So it's just one feature more to interact with the state comparing to LlamaIndex. Let's see the next one, that is Semantic Kernel framework, how it manages the state. Semantic Kernel actually use completely external runtime state management, where developers create state objects and coordinate manually with the framework's orchestration system through callback patterns. The approach requires just manual coordination, as we saw. The only utility is providing clean separation between state management and agent orchestration while allowing custom state management strategies, but of course requiring significant coordination effort. There is an injection point also here in the chat loop. If we go to the chat loop, see that is we can see the state directly here. We initialize the state here. And after this, we don't assess the state from the agent. There is no way to interact with it. And let's see in the tool the same, we don't have any state management. It means that we have to organize everything from outside, okay? Just using a global state like in the AutoGen. We don't see the implementation here because actually it's a way similar to AutoGen. And we have also, of course, the vanilla. We manage all by ourselves, and it's quite similar. It's quite similar with AutoGen or Semantic Kernel. So it's just managed outside. If we go directly to the execution, we can see the state. We get the state directly. We get the state directly from the state file. And for each interaction, we are going to direct the state. At the end, we just see that control versus automation. So external frameworks give complete control over state structure, validation, and flow, but require manual implementation of all coordination logic. Internal frameworks actually provide automatic state management, built-in coordination, but limit direct access, and sometimes it's quite difficult also to understand where I can get the state, in which point, especially if the documentation is not really clear. In LlamaIndex was a little bit difficult to understand where to get it. Also in OpenAI, understanding also that the context management that actually is the state management. Sincerely, I prefer external management. I also like the LangGraph LangChain approach that actually they control the state management and they're using a sort of merging technique that make it quite good, because also you have to consider also that in LangChain LangGraph, all those state changes are saved automatically in the checkpointer in the database, and it's really good to debug, to see all the steps, all the history of each workflow, all the changes of the state, the chronologically changes of the state. So I really appreciate also LangChain. Looking at our state management benchmark, we see the spectrum of trade-offs across frameworks. So LangGraph leads the pack at 46 points, combining high abstraction at 9 with perfect tense in both documentation and flexibility. It provides type-safe automatic state merging while maintaining maximum customization potential, the best of both worlds. OpenAI follows at 40, low abstraction at 3, actually excellent readability at 8, here, simple setup at 7, and maintains high flexibility at 8. It's the framework for teams wanting explicit control without excessive complexity. AutoGen score 39, you can see here, with minimal abstraction at 2, essentially just passing state object between agents. This simplicity translates to excellent readability at 8 and minimal setup complexity also 8. You maintain near complete flexibility at 9 through your sacrifice automation. Two frameworks tie at 32, that is LlamaIndex score, that's a perfect 10 for abstraction, completely hiding state complexity but paying the price with only 2 out of 10 for flexibility. CrewAI presents high abstraction at 8 through its memory layers, but this impacts readability dropping to 5 and severely limits flexibility at just 3. Semantic Kernel trails at 29, struggling with callback-based coordination and scoring lower across most metrics, particularly documentation. Key insight reveal distinct tiers. So high abstraction frameworks split into 2 camps. LangGraph delivers automation with flexibility through excellent documentation, while LlamaIndex provides automation without control. OpenAI and AutoGen offer low abstraction with high flexibility for teams wanting explicit state management. CrewAI and Semantic Kernel struggle with trade-offs that hurt both usability and flexibility. So the recommendation is just choose LangGraph for sophisticated state workflows where you need both power and flexibility. Pick OpenAI for balanced control without complexity. Select AutoGen when you want minimal framework interference. Avoid LlamaIndex for complex state. Its maximum abstraction provides almost no flexibility. And avoid CrewAI state control matters. You are locked into the patterns. It's time to tackle one of the most critical aspects of conversational AI, that is memory management. We'll compare both short-term cached memory and long-term persistent memory storage across multiple frameworks, how each handles this essential challenge. Memory management determines whether your agents can maintain context across sessions, remember previous conversation, and provide coherent multi-turn interaction. Each framework approaches this challenge differently, with unique trade-offs in complexity, performance, and developer experience. Let's start with the vanilla implementation. Actually, it's the from scratch baseline. It serves actually as our baseline for comparing all frameworks. So it demonstrates what developers must build when frameworks provide no memory utilities. So this complete from scratch approach showcases the full complexity of proper conversation memory management, including data structure, storage backends, thread safety, and lifecycle management. This implementation will be our reference point for understanding the level of abstraction each framework provides. When frameworks offer no memory utilities, developers face this same implementation burden. The vanilla implementation begins with a carefully designed data structure that you can find in Session Manager that capture every nuance of conversational AI interactions. This structure forms the backbone of conversation management, providing the semantic richness necessary for sophisticated memory system. The message role enumeration establishes a comprehensive taxonomy of 4 different participants in AI conversation. Beyond the obvious user and assistant roles, the system recognizes system-level messages that provide context or instructions, tool messages that capture the results of function calls, and error messages that preserve information about failures. This granular role system enables the memory system to understand the source of nature of each piece of information, which becomes crucial when reconstructing conversation context or filtering messages for specific purposes. So the central message that we have here, the class serves as a comprehensive container for all conversation elements. Every message receives automatic timestamping through the default factory lambda, ensuring that conversation chronology is always preserved without requiring explicit developer action. So the optional message ID field supports a scenario where external systems need to reference specific messages, while the parent message ID enables conversation trading and branching. We need to understand how the short memory, cached memory, or long memory, persistent memory in database actually works. Okay, let's start with the cached memory. Specifically, we call it in-memory session. That is a class that we find here. The cache memory implementation prioritizes actually speed and simplicity over durability, creating high-performance conversation buffer that maintains recent dialogue context without the overhead of persistent storage. So this approach serves applications where conversation continuity within a session is important, but long-term persistent across application restarts is unnecessary. The memory session class initialization establishes the fundamental parameters for memory management within a single application lifecycle. The max history parameters acts as a crucial performance tuning knob, preventing unbounded memory growth by automatically discarding older messages when the conversation becomes too lengthy. The session tracks its creation and update times, providing basic lifecycle metadata that can be useful for debugging or session management purposes. So each dictionary contains the minimal information necessary to reconstruct conversation flow. Timestamp for chronological ordering, subject to distinguish between conversation participants, content for the actual message payload, and type to categorize the nature of the interaction. So the add message method implements the heart of the cached memory strategy. So when a new message arrives, the system immediately timestamps it and appends it to the history list. The automatic truncation logic then evaluates whether the conversation has exceeded the configured memory limit. If so, the system performs a slice operation self.history with the max history length, efficiently retains only the most recent messages, discarding older entries that might not longer be relevant to ongoing conversation context. So this truncation strategy serves multiple purposes beyond the memory management. And we have also the get recent messages. This method actually demonstrates the cached system ability to interface with the broader application architecture through format conversion. While the internal storage uses lightweight dictionaries for efficiency, this method converts them into comprehensive message object when other parts of the system require the rich data structure. So the conversion process include role mapping logic that translate the simple subject field into properly typed message role and values, ensuring type safety and consistency across the application. We also have other methods, clear the history, get the session stats. So you can also implement from scratch wherever you need to interact with the conversation data. Let's see the persistent session. So the persistent memory actually guarantee the durability with this class. So the persistent memory implementation transforms conversation management into a full-fledged database system, providing enterprise-level durability. So this approach enables conversation to survive application restarts, system crashes, and deployment updates, creating a foundation for long-term conversational AI relationships. Okay, so actually the threading lock ensures thread safety from the moment of object creation, recognizing that modern AI applications often handle multiple concurrent conversations. So the automatic database initialization through init database follows the principle of graceful degradation, so ensuring that the storage system becomes available even when starting from a completely fresh environment. The database schema design reflects deep understanding of conversation management requirement. The sessions table, maintain high-level metadata about conversation instances, tracking creation and modification times that enable conversation lifecycle analysis. The metadata field stored as a JSON text provides extensibility without requiring schema migrations, allowing application to associate arbitrary information with conversation sessions. The comprehensive messages table serves as the backbone for conversation persistence. The auto-incrementing primary key provides fast internal references, while the message ID field with a unique constraint enables external system to reliably reference specific messages. Sequence number optimize the most common query pattern of retrieving recent messages from a specific conversation. The secondary index, session ID, and timestamp supports chronological queries and debugging scenarios where precise timing relationships matter. And the add message method orchestrates, like in the cached way, in the cached memory, in the short memory, the complex process of durably storing conversation messages while maintaining data integrity and consistency. So the method begins by acquiring the thread lock, ensuring that concurrent message additions don't interfere with each other or corrupt the sequence numbering system. The connection is managed within a context manager, guaranteeing proper resource cleanup even if exception occur during the insertion process. The sequence number generation logic demonstrates careful attention to data integrity. By querying for the maximum existing sequence number and incrementing it, the system ensures that message ordering remains consistent even across application restarts or concurrent access scenarios. So the fallback to sequence number 1 for the first message in a session handles the empty table case gracefully. The message ID generation strategy actually creates a globally unique identifier. So this approach ensures uniqueness while maintaining readability by debugging purposes. So the actual insertion operation, demonstrates provide handling of complex data structures. Tool calls are serialized using their two dictionary method and stored as a JSON, preserving the full execution context while maintaining the ability to query and analyze tool usage patterns. So the metadata dictionary receives similar treatment, providing application with flexible extensions points without requiring schema changes. The session metadata update ensures that the sessions table accurately reflects the most recent activity in each conversation. This information supports conversation management features like identifying recently active sessions or implementing session cleanup policy. We have the get messages, and we have also the get recent messages that actually implements efficient conversation context retrieval through carefully optimized database queries. The method begins by determining the total message count for the session and enabling precise calculation of the offset needed to retrieve the last n messages. Okay, this approach avoids loading unnecessary data while maintaining correct chronological ordering. Let's see the session manager, that actually is the unified interface. This class actually represents the culmination of the vanilla implementation architectural philosophy, providing a single current interface that seamlessly bridges the gap between lightweight cached storage and enterprise-grade persistent storage. This abstraction layer enables application to make storage decisions at runtime while maintaining consistent interaction patterns. The session manager accepts a Boolean flag, okay, that determines whether to instantiate an in-memory session or persistent session. Let's see the add user message. When operating in persistent mode, the method constructs a full message object with a comprehensive metadata support, okay, leveraging the database's ability to store rich information structure. So the metadata from the arguments dictionary gets preserved in the database, enabling application to associate arbitrary information with specific messages. In contrast, okay, when operating in cached mode, the method transforms the same input parameters into the lightweight dictionary format expected by in-memory session. So the task type parameters get extracted from arguments and passed directly to the cached backend simpler interface. This dual mode operation ensures that application can use identical calling terms regardless of the underlying storage mechanism. We also have the same way the add assistant message. The only difference is the role. So in this case, it's going to be user. For the assistant, it's going to be assistant. We have also add tool message. We have add agent message. And also another useful method is the get conversation history that showcases actually the abstraction layers most complex responsibility, format normalization across radically different storage approaches. This method must bridge the gap between the rich message object returned by persistent storage and the simple dictionaries used by cache storage, presenting a unified view to calling code. We also have the clear session and the get session stats that dynamically get the right instance if persistent or cached. Actually, the session manager embodies several key architectural principles that make the vanilla implementation robust and maintainable. Let's see the integration with the application runtime. Let's see the chat loop class. We can find the main file is initialized in the main file, but is imported from helpers. So we can find it here. So the session manager initialization demonstrates the power of configuration-driven architecture. So they use persistent parameter, okay? Your persistent memory parameter comes directly from the application state object, enabling user or deployment configuration to control memory behavior without code changes. So the main conversation loop that we can find here in run, as you can see here, before calling each agent, we get the conversation history, okay? And we put the history directly in the prompt, okay? In this case, to perform a tool selection, or in other case, to talk with a specific agent. And every time we process a message, we call this log user method that actually add to our session manager the user message. And when the agent reply to our request, we are going to do the same action with the store conversation. And we are going to actually add an assistant message to our session manager with the response and with also task type that specifies direction type for this specific case. For example, by requesting the last 20 message, the system provides the AI with sufficient context to understand references, maintain conversation threads, and build upon previous exchanges. Okay, let's see the AutoGen frameworks, how it manage actually the session manager. So we can find here the AutoGen framework. the short-term memory and the long-term memory. So this part actually quite easy because AutoGen Core provides zero built-in memory management capabilities. Like vanilla implementation, developers must implement the entire conversation memory system from scratch using the same approach detailed in our baseline implementation. So actually, the AutoGen framework offers agent runtime and message passing infrastructure, but provide no utilities for short-term memory, long-term memory, no persistent storage utility, no caching mechanism, no session ID or thread ID management, no conversation trading or history management, and no built-in serialization or storage coordination. It's just quite fast. There is no framework abstraction level for this feature. Let's see the CrewAI frame. And things here are quite different. CrewAI actually provides a built-in 3-tier memory system, really sophisticated, that handles different temporal and semantic memory needs without requiring custom implementation. So each memory type serves a specific purpose in maintaining agent intelligence across interactions. So let's see the short-term memory. We can see here short-term memory. Actually, it stores the recent interaction and context within a single execution session, maintaining conversation currents during active tasks. The implementation uses RAG with ChromaDB for semantic similarity search rather than chronological retrieval. So this allows agent to find contextually relevant information from recent interactions. Storage is volatile by design, cleared after session completion to prevent information leakage between sessions. We have also entity memory captures information about specific entities, people, places, concepts, and their relationship encountered during tasks, building a knowledge graph for deeper contextual understanding. That's quite cool, right? So, the system uses ChromaDB for semantic search, short-term and entity memory, and SQLite3 for structured persistent long-term memory. So CrewAI's strength is its declarative approach. Developers specify memory components and the frameworks handle storage, retrieval, and coordination automatically. The limitation is reduced control over storage internals and memory policies as the framework abstracts implementation. So let's see LangChain with LangGraph. Actually, LangGraph implements a dual-layer memory approach. Short-term cached memory stored directly in the state object, and specifically here in the messages, and long-term persistent memory through its checkpointing system. So this architecture treats conversational memory as an integral part of state management. Let's see short-term memory, the cached memory. That actually is a main state integration using an annotated messages field that automatically manages conversation history. You can see in detail in the section where we talk about the state management part, but actually the add message notation here append the last message directly from the returning of each agent. If we go to the agent, we see that the return of each agent add a new message in our messages key in the state, and this is just our cached conversation. So this approach means that conversational memory lives directly in the graph state, accessible to all agents during execution. So the add messages function handles the duplication, ordering, and maintains the conversation thread automatically without explicit memory management code. Let's see the long-term memory. That is the checkpointing system. We can find directly in the checkpointer. The checkpoint integrates at the orchestrator level, automatically persisting the entire main state after each interaction. So if we go to the orchestrator agent, you can see the checkpointer here directly. If we activate the use persistent memory, we'll see that the checkpointer will be initialized. The session restoration happens transparently through thread ID configuration, okay? Because when we actually in the main graph invoke, okay, we go directly to the orchestrator agent. Every time we get a new message, if we specify a session ID, it automatically, we put directly in the config, in the configurable as a thread ID, we call session ID, but it's going in the configuration, we have to call thread ID, and and the LangGraph, it will manage automatically When a thread ID is provided, the checkpointer automatically loads the previous main state, including all the conversation history. New messages get added to existing state messages list, and the entire update state gets persisted after execution. So LangGraph's strength is its seamless integration. LlamaIndex provides core memory building blocks but requires significant custom implementation for session management and persistent coordination. So the framework supplies sophisticated memory components but leaves the integration, file management, and session lifecycle as developer responsibilities. This creates a middle ground between AutoGen's complete do-it-yourself approach and frameworks with full automation. LlamaIndex applies the core memory infrastructure but requires extensive custom integration code. Provided by LlamaIndex is the context, is a class with workflow state management and JSON Pickler serializer, the chat memory buffer with an intelligent token-aware conversation management, a simple chat store for conversation persistent with built-in JSON serialization, and memory from the default method with configurable token limits and truncation policies. Let's understand the context and the chat memory buffer. LlamaIndex distinguishes between two types of memory that serve different purposes in workflow execution. If we go to run chat, we will see actually two parts. So if we switch on use persistent memory, we are going to run Agile workflow with those parameters, but if it's not persistent, we just skip the memory parameters. Let's understand why. The context actually, CTX, stores workflow-specific state, intermediate results, and execution method. This includes agent routing decisions, task progress, and any custom data agents need to share during workflow execution. Context actually is always present regardless of memory settings. If we talk about chat memory that we pass to the parameter memory here, it stores the conversation history, okay, with intelligent token management only provide when persistent memory is enabled, allowing agents to access previous conversation and maintain context across sessions. So the persistent memory, let's see the setup persistent memory that we can find in the session manager here. You can see here the function that create the chat memory buffer as a persistent memory. The context persistence happens separately through JSON serialization. And we have to use the serve persistent memory to save on disk our context, okay, our chat memory and context. Let's talk about the cached memory. That is a context-only approach. So if we set the use persistent false, we are going to actually, in cache mode, agents can still share state and intermediate results through the context of object, but conversation history is not preserved between sessions. We have the method restore context from file that is triggered if we use persistent memory. Actually, the context object, okay, maintain references to the workflow definition, enabling proper state restoration across sessions. This allows complex multi-step workflow to resume from where they left off, preserving intermediate results and agent coordination state. So LlamaIndex dual memory approach provides both granular control over conversation management through intelligent token-based truncation and comprehensive workflow state persistence. Let's see the OpenAI Agents framework. Let's see how we manage the memory. We go to OpenAI. Go. So if we use persistent memory, we're going to set up here. The OpenAI implementation demonstrates the highest level of abstraction for memory management. Unlike other approaches that require significant custom implementation, OpenAI's Agents library provides comprehensive built-in conversation persistence that require minimal developer intervention. What OpenAI Agents provide out of the box actually includes sophisticated session management that handles all conversation persisted automatically. The frameworks provide automatic message storage. All user message, agent responses, tool calls, and results are automatically stored without explicit developer action. So we don't see any code that manage the memory. The session state management, complete conversation trees are maintained with proper sequencing metadata. The database operations, all SQLite schema creation, indexing, and connecting management is handled internally. The thread safety built-in locking mechanism prevent data corruption in concurrent environments. and also the schema evolution. Actually, the library handles database schema updates and migrations automatically. So let's see the session initialization. So as you can see here, the memory mode. Let's see the difference between cached and persistent. The cache mode, the session is known in this case. Okay, we are passing the session. When no session is provided, the agent library maintains conversation history in memory only during the active runtime. The framework still tracks messages for the duration of the application execution, enabling agents to refer to previous exchanges within the same session. However, once application terminates, all conversation context is lost. The persistent mode SQLite session, here we initialize this class. When it's provided, the framework automatically creates the SQLite database file if it doesn't exist, establishes the proper database schema for the conversation storage, stores every message to call, maintains conversation threads, enables conversation restoration across application restart. So the critical insight is that developers never interact with database operation directly. So this SQLite session here is a constructor that handles all infrastructure setup automatically. Let's talk about automatic message management through runner integration. So the conversation integrates seamlessly through the runner run interface. Okay. So if we go to helpers file, this part, we can see here, and is integrated here. It means that when the session parameter is provided, run with the session, the framework automatically loads previous context. Okay, so we get the session from here when run chat with usage. We pass directly to the run. So it retrieves all the historical messages, saves the new user message to the database with proper metadata, capture all agent-to-agent handoff, tool calls, and store everything here in the database. It's just developer responsibilities, zero message management. And if we talk about semantic kernel, actually there are no memory utilities for semantic kernels. It's full from scratch implementation. So you have to develop everything from scratch, exactly like vanilla, like AutoGen. It's a little bit crazy because if I have to develop the memory management from scratch and integrate to some abstraction of semantic kernel and AutoGen, it's going to be really difficult. Actually, it was really difficult and catchy to integrate something from scratch inside a predefined design provided from those libraries. It's just additional challenge beyond a pure vanilla approach. Looking at our memory management benchmark, we see a dramatic spectrum of abstraction levels across frameworks. At the top, LangGraph leads with 50 points, offering the best combination of abstraction and control. Seamless state-based memory with checkpointing, earning perfect 10 for both documentation and flexibility, plus improved readability, setup, and developer experience scores. It elegantly integrates memory directly into state management while maintaining maximum customization potential. Close behind at 47, OpenAI delivers maximum abstraction, where a single SQLite session parameter automatically handles all persistence. Just 2 lines of code give you an enterprise-grade memory management with zero configuration. CrewAI follow at 41 with its declarative 3-tier system, short-term semantic search and entity knowledge graph, and long-term persistent, all coordinated automatically. In the middle ground, LlamaIndex scores 33. It provides sophisticated components like a chat memory buffer and simple chat store, but you will still write significant custom code for session management and coordination. More control, more effort. At the bottom, we find AutoGen at 23 and Semantic Kernel at just 19 points. Both provide zero memory utilities. You must implement the entire system from scratch. Semantic Kernel is actually worse because you also face framework integration overhead on top of do-it-yourself complexity. The key insight revealed 3 distinct tiers. High-level frameworks like LangGraph and OpenAI offer rapid development. LangGraph now leads with the best combination of automation and flexibility, while OpenAI provides maximum automation with less control. CrewAI adds powerful declarative features. The middle ground is LlamaIndex, balancing control and convenience. At the bottom, AutoGen and Semantic Kernel provide full control but require vanilla-level implementation effort. Recommendation: choose LangGraph for the best memory management. Powerful feature with perfect documentation, maximum flexibility, and excellent developer experience. Pick OpenAI for minimal code and maximum productivity with zero configuration. Select CrewAI for declarative patterns. Avoid AutoGen and Semantic Kernel if memory management is critical. They provide no utilities and force you to build everything from scratch. Let's benchmark tools integration and management across the frameworks. So tools are the bridge between AI agents and real-world functionality. So they are how agents can perform calculations, generate code, access external APIs, and interact with systems beyond text generation. So let's examine how each framework approaches this critical component, what abstractions they provide, and how they differ from implementing tools from scratch. So this time, like previous features that we saw, we will start directly with a vanilla case. This is important because understanding what tool management entails help us appreciate what frameworks abstract away. So, first of all, we will see the tool function definitions, creating the actual functionality, the tool selection, the parameter extraction, the parameter validation, ensuring extracted parameters conform to expected types and schemas, the tool execution, running the selected tool with the validated parameters, and the result processing, capturing tool output and generating a final natural language response. So each of these steps requires careful implementation in vanilla code, of course, while frameworks provide varying levels of abstraction and automation for these processes. Let's start with the baseline with the vanilla framework. Let's see the tool function definition. Okay, first we need to define the actual tools with their functionality that you can find in the vanilla folder in the tools pie. We have a base tool here. You can see there are some class. The base tool class, okay, serves as the foundation for all tools in our vanilla system. Notice several critical aspects. First of all, manual schema definition. The parameter schema dictionary must explicitly define every parameter with its type, description, and required status. Unlike frameworks that can infer this from function signatures or decorators, here we must manually maintain this metadata. So this schema serves multiple purposes. It guides the LLM in tool selection, enables parameter validation, and provides documentation. We also put explicit example, so the example variable is an array that helps the LLM understand how to use the tool by providing concrete input and output pairs. In frameworks, this might be handled through automatic example generation or built-in prompt engineering, but here we must carefully, of course, craft this example to improve tool selection accuracy. We have also an error handling architecture. Each tool must implement its own error handling strategy, so the standardized return format with success, result, or error and explanation fields you can find directly on the return of each tool. That actually ensures consistent response across all the tools, but this pattern must be manually enforced in every tool implementation. We have also the get metadata here. It's just a method to get all the tool information for the LLM. This is crucial for tool selection. The LLM needs to understand that what each tool does, what parameters it requires, and how to use it. So frameworks often handle this automatically through reflection or annotations. And then we define each tool, adding the base tool, and we define each tool merging the base tool class, and we define all the variables for the tool. So we initialize the class, we describe the specific parameter, we add the description, and we compile everything for each tool. And then we have the run method that we are going to invoke when we enter into the tool execution step. In this file, we have multiple tools, just really simple tools, sum numbers, multiply numbers. We have also a code generator multi-agent tool that is a complex tool that we will see later. Is a sort of a tool that generates code from a prompt. We have also MCP tool adapter and other utilities. But now let's focus on the simple tools. The next step to analyze is the tool selection. The tool selection actually happens through an LLM-based analysis system that must be completely implemented from scratch. This is one of the maybe the most complex aspect of tool management, determining which tool best matches a user's natural language request. So the system must analyze the user's intent, understand the available tools, consider conversation context, and make intelligent routing decisions. So in frameworks, this is often handled by sophisticated built-in systems with optimized prompts, automatic tool discovery, and intelligent routing logic. In vanilla implementation, we must build this entire system, including prompt engineering, response parsing, and error handling. So we are going to see the LLM tool selector class that actually is responsible for this work and is included in helpers py. We can find it here. You can see is a really structured class. As you can see here, it reveals the complexity of tool selection in vanilla system. There is a prompt engineering. We have a create selection prompt method here. This method must manually construct, comprehensive prompts that include the conversation history, tool descriptions, parameters, schemas, and examples. This requires careful formatting to ensure the LLM understands the available option and can make informed decisions. Notice how conversation history is manually truncated and formatted. Frameworks often handle this automatically with optimized context management. We have also metadata formatting. The tool metadata in this case must be manually formatted into human-readable description for the LLM. The code iterates through all available tools, extracts their parameters, and formats them with clear description of required or optional parameters. This formatting directly impacts tool selection accuracy. Poor formatting leads to incorrect tool choices. We have the response parsing. In the select tool method, we must handle the LLM response. We create a prompt and we invoke the LLM with a prompt. We extract the JSON from potentially inconsistent response format and manage various error conditions. So the regex-based JSON extraction that we can find here, JSON match, is necessary because LLM don't always return pure JSON. This is just a really simple approach. You can implement something more consistent, more structured. You can also implement some retry and exponential backoff. Actually, this is really simple, and you can, of course, implement something more sophisticated. We have also the error handling for the JSON parsing failures, the LLM communication issues, and malformed response. For example, the system must gracefully handle cases where the LLM returns unexpected formats or fails to respond entirely. In this case, we just return an error, but we can implement some retry more sophisticated, as I explained before. So the next task that we have to build is the parameter extraction, parsing natural language input. So parameter extraction happens through the LLM selection process, but requires manual validation and type checking. This task involves parsing the LLM's response to extract tool names and parameters, handling incomplete parameter sets, and managing conversational flows where additional information is needed from the user. So the challenge here is that LLMs might return partial parameters, incorrectly formatted data, or parameters that don't match the expected schema. So the vanilla approach must handle all these edge cases manually, while frameworks often provide built-in parameter extraction and validation pipelines. We analyze the function perform tool selection. As you can see here, the parameter extraction process demonstrates several critical challenges in vanilla implementation. First of all, a manual response parsing. So the system must manually extract specific fields from the LLM JSON response, like tool name, parameters, reasoning. We format the conversation history first, and from the tool selector, we invoke the select tools. We ask the LLM to output specific parameters, like a tool, like the parameters, the reasoning, the ask parameter message, And of course, if there is a ask parameter message, we'll have this kind of output and ask the user for more information before executing the tools. The function returns different response, so error or parameter requester or tool execution. We have actually 3 states. And from the select tool, we get this return, this selection. And depending, okay, on the state of the return, like error or parameter request, we have different state that affect the overall conversation flow. This state machine logic must be carefully implemented to ensure proper conversation handling. The next task is the parameter validation, ensuring parameter conform to expected types and schema. So the parameter validation requires manual implementation of type checking and schema validation. This is where we ensure that the parameter extracted from the LLM's response actually match what the tool expects. The system must validate the required parameters are present, check parameters type, handle type conversion, and provide a meaningful error message when validation fails. So the frameworks typically provide sophisticated validation system with automatic type checking, conversion, and detailed error reporting. In vanilla implementation, every aspect of this validation must be built from scratch. We analyze the tool registry class directly from tools, and in this tool registry, actually, we have the validate parameter methods here, and it manually iterates through the tool's parameter schema to check for required parameters. This requires maintaining consistency between the schema definition and the validation logic. Any mismatch can lead to runtime errors or incorrect behavior. We have also, there is a missing parameter detection. The system builds a list of missing parameters by comparing the provided parameters against the schema requirements. This information is crucial for providing meaningful error messages to users and enabling conversational parameter collection. We have also the tool existence validation. So the system builds a list of before validating parameters, the system must verify the tool exists in the registry. This prevents attempting to validate parameters for non-existent tools and provide appropriate error messages. We have also execution time type checking. So the execute tool method, okay, relies on Python built-in type checking. Type check during function execution. So when the tool's run method is called with the incorrect parameters, Python raises a type error, which is caught and converted into a structured error response. This approach provides basic type safety, but lacks of the sophisticated validation that maybe frameworks offer. All error conditions must be manually formatted into consistent response structure. The system maintains a standard error format with success error tool and available tools field to provide comprehensive feedback. Okay, we have also some fallback mechanisms. So when the tools aren't found, the system provides a list of available tools to help the user understand their option. In this case, this kind of helpful error handling must be manually implemented, of course, through the system. The next task is the tool execution, so running the selected tool with the validated parameters, so that the tool execution requires manual orchestration of the entire process. This is where all the previous steps come together. So we take the selected tool, the validated parameters, and actually execute the tool when managing session state, usage tracking, in our case, error handling, and result processing. So the execution phase involves several critical responsibilities: generating unique identifier for taking, executing the tool through the registry, handling both successful and failed executions, managing session storage, and determining whether results need additional natural language processing. So frameworks typically provide execution engines that handle this concern automatically. In our case, we need to implement the function in helpers is underscore execute tools. We can find it here. As you can see here, the system, okay, generates unique tool call IDs for tracking and debugging purposes. This manual ID generation is essential for correlating tool calls with their results in logs and session history. We have also a registry-based execution. The actual tool execution goes through the registry self tool registry execute tool, which provide a level of abstraction but still require manual orchestration. The registry handles tool lookup and parameter passing, but error handling and result processing remain manual. For example, we have execute tool here. So we execute the tool with this method from the tool registry. We add a tool message to the session manager. In this case, we update the usage, but this is just optional. And at the end, we have the success. So if the tool is success, it generates a natural response. If not, we throw an error. And at the end, we add an assistance message to the session manager. That is the final response. So the next step is the result processing. So capturing tool output and generating final natural language response. That actually is this method here, general natural response. And as you can see here, this function must manually construct prompts, also in this case that include the tool name, description, user, original request, the tool's output. This context is crucial to generating relevant, helpful responses that connect the tool results back to the user original intent. The system determines the appropriate format for the result text. This processing actually ensures consistent response. The system also uses predefined template, in this case that is tool result interpreter prompt template that we can find from prompts. Let's see how is the prompt. As you can see here, we are asking to the LLM to interpret tool execution result and provide natural response, giving some variable, okay, the tool name, the tool execution, the user original request, the tool execution result, as a list of specific instruction, and at the end we're going to have the natural informed response. Let's discover the tool registry class that actually is the registry that ties everything together. We can find here in tools. So the tool registry is doing actually a orchestrator job. It serves as a central coordination point for the entire tool management system. First of all, every tool must be manually instantiated and registered with the system. Okay, there is no automatic or discovery registration. Each tool requires explicit setup in the register default tools. We also can register external tool as MCP integration, but we will see later. We have also metadata integration, and the registry pattern provides a single point of control for all tool operation. We also have some methods like list tool, get tools metadata, execute tools, as we saw before, validate parameters, clean up, get MCP tools that we are going to implement in the next step. We reached the end of the vanilla implementation about the tool features, and the pros of the vanilla approach actually is the complete control over every aspect of tool execution. No frameworks dependency, transparent error handling. This is really good for didactic purpose to understand what happened under the hood. And it gives you flexible return formats, full visibility into the entire process, no vendor lock-in, complete understanding of system behavior. But the cons, of course, is a significant boilerplate code for every task, manual parameter schema definition, a lot of work, no automatic type conversion, manual error handling, no built-in state management, requires manual integration with LLMs, complex prompt engineering, manual JSON parsing. It's time-intensive development process. Okay, let's see how the frameworks implement the tools ecosystem. Let's start with the CrewAI. We are going to the CrewAI folder. We start from the tools py. CrewAI takes a completely different approach, leveraging Pydantic for automatic parameter validation and schema generation. We can see the tool definition here. Okay. As you can see here, the Crew agents receive the tools through the tools parameter during initialization. You can see here in the chat Crew, where we define the agent. We are going to ingest the tools using the get tools method from tools file. The framework handles tool discovery, parameter validation, and execution automatically through its agent executor system. This is really simple. It is a high level of abstraction. As you can see here, you define just the tools as a class, some number tools, for example. You merge with the base tool. The base tool class is directly from the CrewAI library. You define all the input parameters directly with the standard Pydantic methods. So field, 3 point, it means it's required. The description, it's quite easy, okay, comparing to the vanilla implementation. And each tool, it has a description. You put the arc schema directly from the Pydantic class. the name, and we have for each tool, required for each tool, underscore run function that execute the tool and give us the response. This is quite good. I really like actually the way CrewAI implement tools. It makes everything so easy. We go into the LangChain LangGraph folder. We can find directly the same tools. So the LangChain approach actually centers around function decorators and state bindings patterns, providing a different abstraction model comparing to CrewAI. As you can see here, we have all the function defined in the tools file. They are just simple function with the variable and the types directly in the parameters in the function input. So what we are doing here, we just define the function above, and when we get all tools, we are applying the tool decorator directly to the function. Okay, so it's going to bound the simple function to a decorator and return the decorated function with all the LangChain and LangGraph utilities. Actually, the LangChain pattern separates the core tool logic from the framework bind. The base function accepts a state parameter. This is really important for our, and that we saw before, the state, and we saw before the state management is we can ingest directly into the tool. The agent integration happens through the LangGraph tool calling system. So when we define the agents, in the run method, we are going to, when we run the agent, we include the tools directly during the run. So we have, in this case, we have get all tools that we saw before. We create a tool calling agent and we pass the tools, with also the state already integrated in the tool. So the LangChain approach actually requires tools to be recreated for each invocation with fresh state binding. So this provides clean state isolation, but requires careful management of tool lifecycle. The pros of this approach actually is flexible state injection, strong separation of concern, excellent integration with LangGraph execution engines, automatic parameter extraction from function signatures. But the cons of LangChain approach actually is a complex state binding patterns. It provides a little bit more articulate, more complexity, and tools and need creation for each run, potential memory overhead from closure creation, requires understanding of decorator patterns. Let's see now the AutoGen, how the AutoGen manage the tool implementation. AutoGen takes perhaps the most complex approach, using runtime introspection to dynamically modify function signature for state injection. So let's see how it manage. We go to AutoGen folder. We go to the tools, and the tools themselves are simple async functions that accept a state parameter. The complexity comes in the integration layer. So we need to create a generation tool agent class that we can find in AutoGen agents. Why we need this class? We need this class actually because we need to dynamically modify function signature at runtimes, removing the state parameter from the visible signature while injecting it during execution. It's sophisticated but complex. This approach, we need to create a wrapper. We need to, the wrapper inspect the signature. We need to clean the parameters. There is another async wrapper that actually inject the state. This is really complex, and AutoGen requires this complexity, especially if we want to get the state inside the tool at the running step. And at the end, it's going to create the tools with wrappers. Let's see the OpenAI agents, how they manage the tool integration. OpenAI agent framework uses a wrapper-based approach that provides context through a dedicated object. If we go to OpenAI tools, we see that actually function tool decorator, we can find over each function, automatically provide the run context wrapper class at the first parameter. So this wrapper contains the execution context and state, providing clean access to system information. So the tool registration is really straightforward, and we apply in the get all tools. And the agent integration passes tools during setup. So if we go to setup handoff agents from the handoff agents file, we see that we are passing the tools to specific agent, in this case to general agent, and we pass the tools directly from the function invocation, directly from the main file. So we are getting the tools at the invocation step at the beginning. And as you can see here, we get all the tools, we pass the main context, and we create the tools that we put as parameters in agent creation under the parameter tools. Okay. In this case, we are not using the context, as you can see here, but maybe we have some case where we want to pass the context to the tools. In this case, we can. And that we can use during the tool execution. The pros of OpenAI approach is that the clean separation of concern, explicit context passing, easy to understand and debug, native async support, and direct agent integration. The problem is that it requires wrapper parameter in all tools, less flexible than other state injection methods, and tied to OpenAI's agent framework, potential overhead from a wrapper object. Let's see the LlamaIndex integration. We go to LlamaIndex folder. Also in this case, we open the tools. LlamaIndex integrates the tools directly into its workflow system using context object for state management. Okay, so we have, for example, some number. Let's see the first tool. It uses actually an annotated types for parameter description and receive a context object for state management. So the context provides transactional state assets through the CTX store edit state. Okay, that we already saw in the state section. So the agent integration happens through the workflow system. So when we go to setup handoff agents, in this case, we get the tools here using the method get all tools. As you can see here is all asynchron. We get all the tools from this method here, and it's quite similar to OpenAI, where we pass an array of tools, of function actually, function that were of function, just normal function, and also we extend the tools with also MCP tools that we will see later. So the integrated workflow system, transactional state management, and clean async pattern, type annotation for documentation, and also natural context passing, it's quite good, and I really like from LlamaIndex frameworks comparing to other frameworks. It requires a little bit understanding of workflow concept. Maybe to assess the complex state is a little bit complex. It's tied to LlamaIndex execution model, and the potential learning curve can be slow for context management. But anyway, the system is quite clean. We have the last framework to analyze, that is the Semantic Kernel, that use a plugin-based architecture with decorator-driven function registration. Let's see the tools in Semantic Kernel. You can see here. And we have for each function. So as you can see, Semantic Kernel organized tool into plugin classes, okay, with each method decorated with the kernel function. So the framework automatically discovers and registers this function. Agent integration is handled through plugin registration. Also in this case, if we go to setup handoff agents, okay, we pass the tools in the directly as a plugin here using the method get all plugin instances that we also define in tools. It returns actually every plugin class, okay, for plugin class in get all plugins. So we need actually to discover and return all plugin class in this module using this loop. The pros of Semantic Kernel is that the clear plugin organization, automatic function discovery, minimal boilerplate, clean separation between tools and agent, enterprise grade architecture. But the cons of Semantic Kernel is that actually required a class-based organization, limited state management option, less flexibility in function signatures, and tied to Microsoft ecosystem patterns. Looking at our tool integration benchmark, we see substantial differences in how frameworks handle one of the most critical features, connecting AI agents to real-world functionality. So at the top, we have a CrewAI that lists with the 51 points, the highest score overall. It achieves this through pedantic power automatic schema generation with minimal boilerplate. Simply define a base model and run method and you are done. Maximum simplicity meets production readiness. Tied for second at 50 points, that is almost equal, we have LangGraph and OpenAI at the same position, taking different but equally effective approaches. LangGraph earns perfect tense for documentation and flexibility with its decorator-based pattern and state binding, maximum customization potential. OpenAI delivers with its intuitive run context wrapper pattern, explicit context passing that's incredibly easy to understand and debug. In the middle tier, we have a Semantic Kernel, scores 43, with its enterprise Grace plugin architecture, clean class-based organization with automatic function discovery. LlamaIndex follow at 40, offering workflow integrated tools with transactional state management, though it requires understanding workflow concept. At the bottom, we have AutoGen score with just 27 points here. The lowest by far. It employs the most complex approach with sophisticated runtime introspection that dynamically manipulates function signatures, is difficult to debug, fragile to changes, and requires deep understanding of Python's inspection mode. The key insight is when vanilla implementation requires manual schema definition, LLM-based tool selection, parameter extraction, validation, execution orchestration, and result processing, frameworks absolutely provide varying levels of abstraction in this case. CrewAI automates almost everything with Agentic, LangGraph and OpenAI balance power with clarity. AutoGen paradoxically adds complexity through over-engineering. Recommendation is just choose your CrewAI for maximum simplicity and rapid development. It's the clear winner for easy of use, but also LangChain and OpenAI, they're almost there, just difference of just 1 point. Pick LangGraph when you need a complete flexibility with excellent documentation. Select OpenAI for clean, debuggable code with explicit context passing. Avoid AutoGen unless you enjoy complex runtime introspection. It's the hardest to work with by a significant margin. Okay, let's start by analyzing how different AI agent frameworks handle the model context protocol, the MCP integration and execution, specifically focusing on the tool integration features. We'll begin with a vanilla implementation to establish our baseline and then explore what abstraction each framework provides for implementing MCP integration capabilities. So starting with vanilla, we see the raw complexity that frameworks attempt to abstract away. Here is how our MCP integration works without any framework assistance. Let's start with the MCP weather class integration. In vanilla mode, as we are responsible for everything, to manually spawn the sub-process processes, manage the standard input and output pipes, and handle the entire JSON RPC communication protocol itself. So the framework provides absolutely no abstraction for MCP server. So the init method follows a critical initialization sequence that cannot be reordered. First, it stored MCP server defaulting to npm weather package, then initialize tracking variables for the subprocess, okay, RPC request IDs, and discovered tools here. We are using for our demo standard MCP weather service. The sequence is crucial because actually start server must complete successfully before load tools, and before load tools can discover available MCP tools, because tool discovery requires an active server connection. So let's talk about the sub-process management in start server. The method handles the low-level complexity of spawning and managing external processes. It creates a popen, okay, sub-process with 3 bidirectional pipes, standard in for sending JSON RPC request to the RPC's MCP server, a standard out for receiving responses, and standard error for capturing error messages. So text through parameter ensures string handling rather than raw bytes, while buff size 1 enables line buffered communication for real-time action. So the attexit.register with a self cleanup is a call that is critical for proper resource cleanup. Without it, orphaned MCP server processes will continue running after Python exits, potentially consuming system resources. The RPC method demonstrates the manual JSON RPC 2.0 protocol implementation that frameworks handle automatically. Each request requires a unique ID for the response matching. The incrementing RPC ID ensures this uniqueness. So the request structure must be perfectly compliant with JSON RPC 2.0. Identifies the protocol version. ID enables a request response correlation. The method specifies the MCP operation like a tools/list or tools/call, and params contains method specific data. The communication pattern is strictly synchronous. Write a complete JSON request with a new line delimiter. Flush the buffer to ensure the immediate transmission. Then block on a read line until the server responds. This blocking behavior means vanilla implementation cannot easily handle concurrent MCP operation without trading complexity. So the new line delimiter is crucial. MCP servers expect line delimited JSON, and missing delimiters cause protocol parsing failures that are difficult to debug. After this, we can analyze the MCP tool adapter. Actually, additional, you need a custom adapter classes to bridge MCP tool schemas with your application tools interface. This is where the complexity truly multiplies in vanilla implementation. MCP server expose tools using JSON schema for parameters, specific naming convention, and structure response formats. Your application likely uses a different tools interface, perhaps snake case naming, custom parameter validation, or specific error and pattern. So the MCP tool adapter class solve this impedance mismatch. We have the init here. Actually, it stores references to MCP connection for making tool calls. This second line actually keep original MCP tool name for server communication. This part translate MCP tool metadata to match our application tool interface. And this part is a convert schema, is a critical schema conversion, MCP user JSON schema. We need our format. This maps MCP input schemas to our parameter schema structure. So we have also the convert schema function. The convert schema method handles one of the most complex aspects of MCP integration. JSON schema supports a rich parameter definition with types, description, constraint, and required field specification. Your application needs this translated to its own parameter form. The method must extract properties, parameter definition, identify a required field from the required array, and map JSON schema types to your type system. Complex schemas with nested object array parameters or conditional constraints require sophisticated parsing logic that can easily exceed 100 lines of code for full complex. And after we have our execution method using the run function defined inside the MCP tool adapter that actually is executing the selected tool. So we are going to use the MCP connection, call tool method, and we are going to pass the tool name and the arguments. And depending on the result, we are going to return specific information. The call tool method we can get directly from MCP connection from the previous class, and as you can see here, it returns RPC tool/call method with name and arguments. So as you can see, the vanilla implementation shows what every framework is ultimately doing under the hood, but they spare you from writing this extensive infrastructure. Complete vanilla MCP integration often requires more than 500 lines of protocol implementation, schema conversion, error, and resource management code frameworks providing a single function call. Let's see how the frameworks manage it. We start from AutoGen. In AutoGen actually takes a significantly different approach. Rather than manual protocol management, it provides high-level abstraction. We can see it directly in the AutoGen runtime. Actually, the MCP server tools is doing the tremendous work behind the scenes. Actually, AutoGen automatically spawns the subprocess, manages the connection, handles graceful shutdown when needed. All JSON RPC communication is handled internally, and AutoGen sends the initialization and shake, discovers available tools using tool list, what we saw before with the RPC. It uses also the JSON schema for parameters, while AutoGen uses its own tool format. The framework automatically converts between these schemas, mapping types, description, and required fields. The error handling is also managed. Connection failures, protocol errors, and server crashes are handled gracefully with a meaningful error message. Is an async integration, so the entire process is async aware, fitting naturally into AutoGen's event-driven architecture. So the result is a dramatic code simplification. What required hundreds of lines in vanilla becomes a single function call. However, this abstraction means you lose some control over the connection details and they're specific. So we register the MCP tool directly in the register method, directly in the router agent, using the router agent here register that we can find directly here. So when we invoke the register method in the router agent, we are actually passing MCP tools with the parameter workbench tools. The runtime handles agent lifecycle to route executing context. When an agent needs to call an MCP tool, the runtime manages the actual server communication transparent. Actually using Lambda, so the MCP tool get here, get MCP servers directly from the tools, directly from the agent runtime. And here we go. So this design means that from an agent perspective, calling a weather API through an MCP is identical to calling any other tool. So the complexity is completely abstracted away. However, AutoGen provides moderate flexibility. You are limited to the server types and configuration that MCP server tools support. Let's see how CrewAI manage the MCP integration for tool execution. We go into the CrewAI folder. We get the tools by. As you can see here, CrewAI takes a slightly different approach with its adapter path. Let's focus on the initialize MCP server. As you can see here, the adapter pattern provides a sophisticated abstraction layer with several key advantages. The tools property doesn't immediately connect to the server. Okay, instead, it establishes the connection only when tools are first assessed, improving startup performance. The MCP server adapter that you can find here manage the underlying subprocess and JSON RPC connection internally, providing connection reuse and automatic recovery from connection failures. The tool collection integration wraps MCP tools into its tool collection that you can find here, which provide additional features like tool filtering, validation, and execution tracking. So the adapter pattern, so the framework stripped away the JSON RPC protocol like AutoGen, but provide the adapter as a separate abstraction layer. It returns directly MCP tools. Also the cleanup MCP server, we need it when we stop the workflow directly here. We can see directly in the main. So when the main process is closed, we're going to clean up all the MCP servers. So we have to integrate this on the main execution. And we are passing directly the tools as a normal MCP tools, and then our parameter is true. If we want to include MCP, we initialize MCP server, get the tools, and extend MCP tools. Okay, let's see LangChain now. So let's see how LangChain and LangGraph manage the MCP client integration. Actually, they takes another approach. Go to the tools files. They actually using a dedicated MCP adapters that we can find from the import here. They are using load MCP tools, standard input-output server parameters, and the client session. Let's go straight to the function, to the async function, load MCP weather tool. Actually here, this is a little bit sophisticated integration that balance standards compliance with the framework integration. Unlike other frameworks that implement their own MCP clients, LangChain uses the official MCP Python library. Okay, this ensures that the full MCP specification compliance and access to all protocol features. The nested async context manager Studio Client, standard input-output client, and client session provide proper resource management, and standard input-output client manages the sub-process lifecycle while the session handles the JSON RPC connection. The load MCP tools, okay, from LangChain MCP adapters converts MCP tool schemas into LangChain tool format. This bridges to different ecosystems while maintaining compatibility. We have also session.initialize here. That is a call that performs the MCP handshake, including capability negotiation and server information exchange. This is handled automatically by the official client. This is an async first design, so the entire integration is async native, fitting well with LangChain modern async architecture and allowing for efficient concurrent tool load. So this approach provides the highest level of MCP integration compliance while still providing the convenience of framework integration. However, it requires understanding both MCP contexts and LangChain tool system. We need this wrapper here, that is create sync tool wrapper. This pattern addresses a fundamental architectural mismatch between MCP and LangChain. The MCP is inherently asynchronous built-in. Asynchronous is built on JSON RPC over streams, while LangChain tool system is traditional synchronous. So the wrapper runs async mode in a separate thread to bridge this gap. The schema preservation, so the wrapper maintains all tool metadata, okay, name, description, parameter schema from the original MCP tool, ensuring that LangChain agent receive complete tool information. We also a thread management in a run async in thread that you can find it here. It handles actually the complexity of running async code in a synchronous context, managing event loops and thread lifecycle automatically. As you can see here, the method is defined here, and you manage the loop with the async IO. So the advantage is standards compliance using official MCP libraries, but the disadvantage is the async/sync impedance mismatch require additional wrapper code. So let's see how LlamaIndex implement the MCP tools integration. Actually, LlamaIndex provides a built-in MCP integration through the LlamaIndex.tools.mcp module that we can find here from the import in tools by file. It offers actually a streamlined approach that emphasizes simplicity and tool collection unification. Everything is included in get MCP tools, and the basic MCP client class actually abstracts away the sub-process management and the JSON RPC communication complexity. Like vanilla implementation, you don't need to handle a standard input-output pipes or protocol details manually. We have a unified tool loading using the add tools from MCP URL. This is a function that is a sort of tool converter. It connects to the MCP server via the provided client that we pass as a parameter, and discovers available tools and automatically converts them to LlamaIndex function tool format with proper schema mapping. The client also accepts standards input and output parameters, but wraps them in LlamaIndex abstraction layer. As you can see here from the function, actually, we get the weather MCP server configuration here. We pass the node package, executor, the auto install weather server. It inherit all the environment and API key. Here actually is a empty URL since we are using this STDIO client and not HTTP in this case. And we pass configured client for server communication. Actually, this is a transparent tool mixing. MCP tools are headed to the same list as a native function because get MCP tools is invoked here in the general get all tools, and we extend the tools, okay, with the new MCP tools we got from the MCP utilities from the MCP server. It's also async aware integration, so the entire tool loading process is async native. as you can see here, using await inside an async function, is allowing actually efficient concurrent loading of multiple MCP servers. It has a runtime tool discovery, so tools are loaded at runtime rather than configuration time, enabling a dynamic MCP server discovery and hot swapping of available capabilities. So the advantage of LlamaIndex approach is simplicity and seamless integration with LlamaIndex function calling architecture. Okay, let's see the OpenAI first class MCP support. We go to the OpenAI folder. Actually, OpenAI's integration demonstrates the gold standard of framework MCP support. MCP servers are treated as native agent capabilities, not add-ons or extensions. So the MCP server's parameter is built into the core agent class. As you can see here, we go directly to the head of agents, and we see there is directly the MCP server parameter. Actually, it makes the MCP integration as a fundamental as tool integration. There is a zero configuration integration, no adapters, wrappers, or protocol implementation needed. OpenAI's SDK handles all MCP complexity intern from sub-process management to JSON RPC communication to tool discovery. There is also a transparent tool execution. From the agent perspective, MCP tools are indistinguishable. MCP tools are treated like exactly native tools, so the SDK automatically routes tool calls to the appropriate MCP server and handles a response formatting. Results are built-in error handling that manage connection failures, server crashes, and protocol errors, and also model integration because the MCP tools are automatically exposed to the model using OpenAI's native function calling format, ensuring optimal performance and compatibility with the GPT model capabilities. The MCP server here are passed to the setup and of agent that we actually invoke from the main file. We are passing directly MCP server here. Okay? The MCP server is created as on the initialization of the main process. We use the get MCP servers, that is an asynchronous function, okay, that we get directly from the MCP servers file that we define here. And as you can see here, it's just initialized using the MCP server standard input-output class, okay, directly from the agent.mcp. Despite OpenAI's advantage integration, the server configuration remains familiar and standardized. We use this class as other frameworks, demonstrating actually MCP successful standardization across the ecosystem. The server inherits the current environment and inject specific configuration. In this case, we use the Node.js package executor, the auto-install weather server package, inherit the current environable variables, and inject the weather service credentials. So the power of OpenAI approach is that this familiar configuration is all you need. So the SDK handles everything else invisibly, making MCP servers as easy to use as native OpenAI functions. The advantage is simplicity and native integration, though the disadvantage is framework dependence. You are tied to OpenAI's agent ecosystem and model providers. So let's discover the semantic kernel. We're going to be really fast because actually there is not any capabilities, any utilities in semantic kernel. So you have to integrate all from scratch. In our case, there is not an integration yet, but you can use exactly the same in vanilla approach. Okay, you have to implement everything from scratch and pass as a tool. So here we go. Now it's time for MCP server integration benchmark. At the top, OpenAI leads with 51 points, offering superior MCP support with minimal configuration. MCP servers work as near-native agent capabilities. Pass an MCP server's parameter with simple setup and everything works smoothly. So minimal adapters, wrappers, or protocol code needed. This reduces vanilla's 500 plus lines to streamlined configuration. Tied at 46 points, AutoGen and LlamaIndex both deliver excellent high-level abstractions. AutoGen's single MCP server's tools function replace hundreds of lines of sub-process management and JSON RPC protocol code. LlamaIndex basic MCP client with the unified tool loading creates seamless integration where MCP tools become indistinguishable from native functions. Both frameworks reduce complexity by 96%. Tied at 42 points, we have CrewAI and LangChain LangGraph. CrewAI uses an adapters pattern approach, provides clean separation between MCP protocol and CrewAI's tool ecosystem. Features like lazy loading, connection pooling, and global caching make it robust for production. LangChain LangGraph also scores 42 with improved MCP integration. It uses the official MCP Python library for full specification compliance and maximum flexibility. The improved score reflects better async bridging patterns and cleaner context management compared to earlier implementations. It's now competitive with CrewAI while maintaining superior flexibility. At the bottom, Semantic Kernel scored just 90 points, of course. It provides zero MCP utilities. You must implement sub-process management, JSON RPC protocol, schema conversion, and everything, clean up everything from scratch, exactly like vanilla development. Worse, you also face additional complexity adapting to semantic kernel plugin standards, so it's actually more complex than vanilla. Recommendation is choose OpenAI for minimal configuration integration, 51 out of 60, if framework lock-in is acceptable. So pick AutoGen or LlamaIndex for powerful single function abstraction with framework flexibility. Select LangChain LangGraph when MCP specification compliance matters and you want maximum flexibility. Improved implementation makes it competitive with CrewAI. Choose CrewAI for the adapter patterns, cleaner separation, and avoid semantic kernel entirely for MCP integration because actually it doesn't have MCP integration. In this section, we are examining for specific small features that are common requirements in production agent systems is executing code generation agent, enforcing structured JSON outputs, tracking token usage for cost management, and implementing safety guardrails. So we will see how each framework approaches these problems and what level of abstraction they provide compared to implementing everything from scratch. Let's start with the first feature, that is the code execution for generated test. This project includes a code generation multi-agent system, as we saw before, with a three-step workflow that is a coder, tester, and reviewer agents working together. We want to analyze the agent orchestration, state management, or patterns here because they follow the same principles we've already covered in the main agent orchestration benchmarks. Those same patterns and scores apply. What we are examining now is one specific utility. How do frameworks execute the generated test code? After the tester agent generates unit tests, the system needs to actually run those tests in a safe, isolated environment and capture the results. This is important because executing arbitrary AI-generated code requires isolation, proper error handling, and timeout management. And you can see here in the code generator, we have a coder, a reviewer, and tester. So the coder agent actually receives user requirements and generates Python code. It considers previous failures and review feedback to improve the code with each iteration. The tester agent is the second step that takes the generated code and creates comprehensive unit tests, and it then executes this test to verify the code works correctly. And the reviewer agent that actually analyzes both the code and test result. If test pass, it approves the implementation. If test fail, it provides detailed feedback to the coder agent explaining what needs to be fixed. Let's see the test execution feature. So the critical moment comes after the tester agent generates the test code. The system needs to actually run those tests and capture the result. Let's see how each framework handles this code execution. So in the vanilla implementation, as you can see here in the tester, we have this part. So the subprocess.run call here launches a separate Python process that runs the unit test module as a command line in the directory containing the generated code and test. So the capture output set to true parameter collects both standard out and standard error streams so we can parse them later, while text equal to true ensures the output comes back as a string rather than bytes. So the 30 seconds timeout prevents infinite loops or hanging tests from blocking the system indefinitely. However, this subprocess still runs in the same environment as the main process with the same file system access and system resources. There is no containerization or sandboxing, so malicious test code could theoretically read sensitive files or make network calls. Then we parse the unit test output manually here in the vanilla code using this function that is parse test output. So we can see here. This parsing function actually implements about 70 lines of text processing to extract the structured test results from unit test human readable output format. It handles two different output patterns depending on the return code. For successful runs, it parses the runX test line to count past tests, while for traceback information, the state machine approach with collecting trace and trace lines accumulate multi-line error messages correctly. So this manual parsing is necessary because unit test outputs plain text rather than structured data formats like JSON or XML. So the process that is just a simple subprocess call works anywhere Python runs, no additional dependencies, direct control over execution. Let's see the AutoGen implementation. So AutoGen actually, let's find the specific section that we can find here. We can find directly in the tester inside the AutoGen folder. We go to the specific function run test with Docker. So AutoGen provides Docker-based code execution through its extensions. As you can see, the function AutoGen create a fresh Docker container running Python 3.12 Slim for each test execution, providing complete isolation from the host system. The Docker command line code executor manages the full container lifecycle, including startup, volume mounting of the working directly, and cleanup. The test code is passed to Python code execution tool, which executes inside the container and captures standard out, standard error, and exit codes. The finally block ensures the container is properly stopped and removed after execution, preventing resource leaks. This provides true sandboxing where generated test code cannot access or modify the host file system, making it safe to run trusted AI-generated code. Notice that the parsing logic remains the same. AutoGen still uses the vanilla parse test output because actually the unit test output format doesn't change. The process is complete isolation via Docker, tests run in a clean container environment, automatic container cleanup, and cannot affect host system, and also built-in timeout handling. The cons are that requires Docker installations, lower than subprocess due to container overhead, still requires manual output parsing, more complex setup than vanilla async execution required. If we talk about CrewAI implementation, actually, CrewAI doesn't provide code execution utility, so implementation is identical to vanilla, so we skip this part. And also LangChain doesn't provide code execution abstraction. The implementation, the same, matches vanilla. And the same for LlamaIndex. Actually, we have only AutoGen until now. So all CrewAI, LangChain, LangGraph, and LlamaIndex doesn't provide any executor, any code executor. And also OpenAI doesn't provide the code execution utility. In those cases, we have to implement something external. We can use the vanilla approach or use other different libraries. The same also for Semantic Kernel. So actually AutoGen is the only one that offers a specific method for code execution isolation. So let's see the second feature, that is structured JSON output. Let's focus specifically on how framework handles structured JSON output enforcement. Let's see the vanilla approach. We can refer to this section of the reviewer. And in vanilla Python, structure output is entirely manual. So every agent that expects structure output needs this exact boilerplate code. Try to parse JSON from the LLM response, extract specific fields using dictionary get, like in this line, with fallback defaults, and catch JSON decode error here. This is a pretty standard method, and is used in this case to handle malformed responses. There is no type safety because you are working with the raw dictionaries and strings, no validation that required fields exist, and no enforcement that field values have the correct types, strings, integers, or booleans. So let's see AutoGen approach. And we can skip because also AutoGen doesn't provide any structure output as core level. Okay, let's see CrewAI. Actually, CrewAI supports Pydantic models for structure output. If we see here, this approach is significantly cleaner. You can see here we define this class with the base model. CrewAI handles the entire validation pipeline internally. When you pass a response format, okay, we define the class with the types here, and we pass actually inside the agent kickoff, we pass directly the base model, the classes directly here that with the code generation response class. CrewAI actually instructs the LLM to return JSON matching the Pydantic schema and automatically parses and validates. If the LLM returns malformed JSON or data that doesn't match the schema, CrewAI handles retries internally before returning the result. You still need to check if the result exists and has the Pydantic attribute. But once you have it, you are guaranteed type-safe access to validated fields. So this is really good actually. Actually, Pydantic is the standard to parse the LLM outputs. The Pydantic integration provides type safety, less boilerplate than manual JSON parsing, and validation happens automatically. Let's talk about LangChain. At the core, you can use the with structure output on certain LLMs, but it's not integrated into the agent execution by default. But anyway, you can apply directly to the LLM. It provides this method on chat models actually, and wraps actually the LLM to automatically enforce a Pydantic schema on all responses from that point forward. So we have the Pydantic schema here, we pass as argument, the class is here, and we describe all the variables and types. When you call invoke on the wrapped LLM, it returns a fully validated Pydantic object instead of raw text, eliminating the need for manual JSON parsing. However, this isn't used in the standard LangChain agent pattern shown in the codebase, suggesting it's an optional utility that developers need to explicitly adopt rather than a built-in feature of the agent workflow. So the method is available, but requires knowing about it and integrating it manually into your agent code. LlamaIndex, you still manually parse JSON like in vanilla approach. And actually OpenAI provides the cleanest structure output. We define the base model class with our variable, with our keys and the types in the JSON. And let's go to the agent. When you run this agent, OpenAI's API ensures the response matches the Pydantic model. So you pass directly here in the agent. There is no JSON parsing code, no try except blocks for malformed response, and no manual validation logic anywhere. So the final output is already a fully validated output Pydantic instance with type-safe attribute access. This works because OpenAI structure output API uses JSON schema to constrain the model's token generation at the API level, mathematically guaranteeing that the response matches your schema. So the Agent SDK integrates this seamlessly, so you just define output type in your agent configuration and get validated objects automatically, eliminating an entire category of parsing errors. Semantic Kernel doesn't show structure output enforcement in the provided code. Cancel. And Semantic Kernel doesn't have any utilities about JSON validation, JSON parsing enforcement. Let's see the next feature, that is the token usage tracking. So the token tracking is essential for cost management and monitoring. Let's see how each framework handles it. We start from the vanilla implementation. So we start from the method called API call with usage. Is a function that we can find here that actually collect all the metrics from the API call. So the request, the input tokens, output tokens, total tokens. Then in the orchestrator, we manually update states and we put this data inside the states. And when displaying to user, we're going to calculate also, we perform this calculation here, and we give the final calculation for the single metrics for this turn and cumulative for the whole session. So the vanilla implementation requires storing the previous turn token counts, calling the LLM, capturing the new cumulative totals, manually calculating the delta for just this turn usage, and then computing cost by dividing token counts by 1 million, multiplying by the per million pricing rates. But it requires discipline to capture before, after snapshot at every interaction point. All cost calculations are manual, requiring you to maintain up-to-date pricing information and implement the arithmetic yourself, which can become complex when dealing with different models or tiered pricing. The same for AutoGen. AutoGen requires manual token tracking from the response object. This is essentially the same of vanilla. So let's see CrewAI. Actually, CrewAI provides the usage metrics in the result object. We use this function, update usage from CrewAI, and it automatically actually tracks the token usage across the LLM calls that occur during the agent's kickoff execution, including any internal retries or multi-step reasoning. So the framework aggregates these metrics and provides them in the result usage metrics. Okay, so in the usage metric, we have all the information stored by CrewAI, and we get here calculate the usage metrics, and the usage metrics is directly the total usage metrics directly a class provided from CrewAI types from CrewAI libraries. Let's see LangChain. Actually, LangChain provides the get OpenAI callback if we use OpenAI. For this specific case, if we use the provider OpenAI, we can see here the get OpenAI callback actually is a context manager that automatically intercepts and tracks all LLM calls that occur within its scope, okay, including any retries or nested calls. So you don't need to manually extract usage from individual response object because the callback accumulates everything automatically. So the callback even includes built-in cost calculation via using cb.total_cost here, total tokens and total cost here, the same. Using OpenAI, let's see LlamaIndex. Actually, LlamaIndex uses the token counting handler that we can find here in this part. You see the code here. So the token counter is attached to the LLM instance and tracks all the call, is injected in the main state with the token counter key, and then we pass the main state directly to the agent. After execution, extract usage we can find here in this function. Let's see OpenAI. That OpenAI agent tracks usage actually is a native implementation. If we go to this code block, we can see that the code result here with the runner.run. So actually we have extract usage from results. So the OpenAI Agent SDK includes usage information, okay, directly in the code result from the runner.run response, returned by providing standardized access through the usage summary attribute. Okay, if we go to see this function, extract usage from result, that we can find in the context here, we get the result and we can get directly the usage summary. We get the usage and we get everything here, the input tokens, output tokens, and everything. Actually, this is more structured than LlamaIndex token counter. You still need to write extraction helper functions, manual call them after each agent execution, update your own state management system to accumulate usage across the session. So the verbosity is similar to vanilla Python, but at least the data structure is consistent across all agent types. And talking about semantic kernel, it doesn't provide automatic token tracking in the code, so need to implement manually vanilla. Let's see the last feature, that is guardrail and safety. So content safety is a requirement for production system. Let's see how frameworks approach this. The vanilla implementation, we start from this function that is called check content safety. We have here, we define this function and actually we call it before processing. So before the process message, we call that function check content safety. So is at the top of the workflow. So the process message function explicitly calls the content safety check before any other processing occurs for user input. This is about 60 lines of safety, checking code, including the prompt construction, LLM API call, JSON parsing with Markdown cleanup. This is just a simple cleanup. You can integrate, of course, more sophisticated with also retries, error handling format response, category classification, and user-friendly violation messages. So the implementation defaults to allowing content of any error to prevent false positive from blocking legitimate user. This pattern needs to be repeated at every entry point where user content enters the system. The pros, of course, is complete control over the safety logic, can customize violation messages, explicit error handling, but is very verbose, repeated across multiple entry points. The AutoGen implementation, actually in AutoGen, the same is exactly we have to implement from scratch, but in AutoGen we put directly as a part of the router agent. If we go here, we define the same function, but we put the handle user message. This is integrated into the router's message handling, and it's directly into the router's message handling flow using the message handler decorator. Every incoming user message, so the routing agent, as you remember, is the first step of the flow. So this callback function handle user message is on top. So first of all, we check the content safety exactly with the same function that we just saw in the vanilla code. CrewAI also doesn't have explicit guardrail implementation, so we must create as a dedicated safety agent, and we call it content safety agent here. No, here we go. We create as a autonomous, as a single agent, and we include in the Crew workflow here. The content safety agent is included as the first agent in the Crew agent list, ensuring it can be consulted during the workflow execution. CrewAI sequential process and agent delegation system will route a request to the safety agent when content needs to be checked. However, unlike OpenAI's automatic guardrails that we will see in a few minutes, you still need to explicitly implement the safety analysis logic within the agent's goal and backstory, and manually trigger the safety check through task dependency or agent delegation. So the safety agent acts as a standard crew member rather than automatic input intercept. This approach could have a lower level of security because actually is executing in parallel. Is a choice between them, and if the if the crew does make a mistake, it doesn't recognize that it's a content safety agent, it just passes directly the flow to another agent. So maybe it's less robust than the other approach when you put the content safety agent on top of the workflow. So the process that it fits into the CrewAI's agent pattern can be part of the workflow, so it's clean, talking about the code and the logics, but no built-in safety utilities still requires implementing safety logic, adds another agent to manage. Let's see the LangChain. LangChain implements safety as a separate agent in the graph, so it's the same paradigm, is the same concept of CrewAI, because we need to create an agent that is called content safety agent, and we put directly in the graph, in the orchestrator agent that is our graph. And actually, the check is implemented as a dedicated node. This is the node. It's positioned immediately after the start node. The content safety here, and if we see the edges, is the first one is the start, and right after we find the content safety. The additional edges method defines the routing logic based on safety check result. So if the content is inappropriate, the graph routes to a safety termination node that ends execution. If content is safe, it proceeds to the routing agent. This graph-based approach makes the safety flow explicit and visible in the workflow structure, though it requires more setup code compared to decorator-based approaches like OpenAI guardrails. This is good because it's integrated into the graph workflow, clear routing logic, you see clearly what's happening, and structure safety result. But the cons is it still requires manual JSON parsing, verbose agent setup, graph routing adds complexity. The LlamaIndex implements safety using a specialized agent, so the logic is the same. We call it guardrail agent. We can find here in the agent definitions, And with output class, actually here the content safety result enforces structure output for safety results, so we can also classify or get other information from the prompt. The agent is included in hands off, of course. It's just conditionally added to the agent list based on the enabled content safety params. We just put a guardrail agent directly here. If the main step enable content safety, we also add the guardrail agent. The router will need explicit end-of logic to delegate to the guardrail agent for safety checks before processing user input through other agents. So this pattern integrates safety as a part of the agent collaboration workflow. OpenAI provides input guardrails as a first class feature. Okay, so we go to the, so we create the logic here with the content safety output. We create the Pydantic model, the output. We define actually how we want to integrate the output. We want to structure the safety guardrail. We define also the function here, content safety guardrail. But as you see, there is a specific decorator. So the guardrail is attached by assigning it to the agent input guardrails. So we are going to put directly as a key, okay, inside the routing agent and execute automatically before the agent main logic runs. So this is quite clever because it's implemented but give you the full customization. So if the guardrails trigger, the OpenAI SDK immediately stops execution and raises a guardrail exception, preventing the potentially unsafe. So if we catch the guardrail exception, here is not implemented, but of course we can catch this specific exception, we can prevent potentially unsafe input from reaching the agent. So this declarative approach eliminates the need for manual safety checks scattered throughout your code, as the framework handles the interception and exception flow automatically. This is actually, I think, the best approach because it's declarative guardrail attachment, it structures safety output, and automatic execution before agent processing. Framework handles exception. Talking about semantic kernel, it doesn't show any explicit guardrail implementation in provided code. So in this case, you also have to implement from scratch following the semantic kernel design. Looking at our benchmark for code execution, starts structure output, token tracking, and guardrails that we call just other small feature benchmark, we see LangChain leading with 48 points, earning perfect 10 in both documentation and flexibility, like always, plus improved readability and setup score. So LangChain's strength is its best-in-class token tracking, the get OpenAI callback, context manager automatically capture all LLM calls and even calculate costs for you. So the gold standard for monitoring spend. It also offers with structure output, utility, and graph-based safety routing, combining powerful feature with maximum customization potential. The improved score reflect better implementation patterns and developer experience. OpenAI follow at 44, so actually are very similar, excelling at structure output and guardrails as we saw just a few minutes ago. The output type parameter mathematically guarantees valid Pydantic object with zero parsing code. Input guardrails attached via simple decorators, executing automatically before any agent logic. It's a very polished developer experience for this feature. And then we have the CrewAI scores 41 points with excellent Pydantic integration through response format and automatic usage metrics collection. So the pattern is declarative and clean, though safety checks require manual agent coordination. In the middle, we have LlamaIndex at 35 that requires more manual work, complex markdown extraction for structure output, manual state management for token counting, and explicit end-of logic for safety checks. AutoGen score at 33, but as one killer feature is the Docker-based code execution, as you remember. It's the only framework provided through sandboxing for running untrusted AI-generated code. Everything else is vanilla-style implementation. At the bottom, we have semantic kernel scores 29. It provides essentially zero utilities for these features. So LangChain leads overall with the best combination of utility support, documentation, and customization flexibility, especially excelling at token tracking with automatic cost calculation. Choose OpenAI for cleanest structure output and guardrail experience, AutoGen if you need Docker-based code isolation. Avoid, of course, semantic kernel unless you specifically need its multi-provider plugin architecture. It offers the least utility support while adding framework overhead. After evaluating 6 major agent frameworks and also the vanilla case across 6 feature categories, the numbers don't lie. Here are the final rankings highlighting clear winners, some surprises. So now you can pick up the agent framework that is perfect for your next project. Let's review which frameworks actually deliver and which ones are better left as academic curiosities. Looking at our overall score, we have a clear picture. So Tier 1 production leaders, the LangChain LangGraph with 284 points, the highest overall score, excelling in memory management, agent orchestration, and offering maximum flexibility and really good documentation. OpenAI Agent with 277, a very close second, dominating in MCP integration with excellent developer experience. And then we have the tier 2 that are just solid contenders, that is CrewAI LlamaIndex, CrewAI with the 249 points, the rapid prototype champion, best tool integration score, and LlamaIndex with 227 points is a balance across all feature, no major weaknesses. And the tier 3 is a specialized framework, AutoGen with just 195 points, great for specific use case but challenging developer experience, Semantic Kernel with 178 points, enterprise patterns but lacks critical utilities. After building production systems across all these frameworks, my personal choice is LangChain LangGraph. Let me explain why. Reason 1, maximum flexibility without compromise. It's core perfect 10 in flexibility across multiple categories, agent orchestration, state management, and other features. This matters enormously in production. Real-world applications always have unique requirements that don't fit cookie-cutter patterns. With LangChain, I can customize deeply when needed. I can drop down to lower abstraction levels, override behaviors, extend components, all without fighting the framework. Other frameworks force you into their patterns. LangChain adapts to yours. Reason 2, perfect documentation. This is sometimes you underestimate this feature, but it's one of the most important. The perfect tendency documentation across multiple categories aren't just about quantity, it's about quality. Okay, every concept is explained with clarity, with example, real use case. A complex pattern like state machine, checkpointing, graph-based workflows are documented with excellent examples. When I encounter issues, the documentation actually helps me to solve them. Or you can also use the AI to solve if you give the documentation as a context or also as a MCP tool. You have to try because it's really a good developer experience. The community is massive. Stack Overflow question, GitHub discussion, community tutorials. If you are old school, you can go to Stack Overflow. If you are future-oriented, you use AI. Anyway, there is always someone who solves similar problems. This reduces debugging time dramatically. Reason 3, transparency and control. This ties into my philosophy about abstraction. LangChain architecture is transparent. I can understand what's happening under the hood. This is the most important thing. State machine model in LangGraph is explicit. I define node, hedges, conditional routing, and state transformation. There is no magic, no black boxes, no wondering why an agent behaved unexpectedly when debugging production issues at 2 a.m. This transparency, believe me, is invaluable. I can trace exactly what happened, where state changed, and why a decision was made. Reason 4, consistent excellence. Looks at the score, 48 orchestration, 50 tools, 46 state, 50 memory, 42 MCP, 48 other features, totaling 284 points, the highest overall. LangChain doesn't just excel in one area, it maintains excellence across the board. This consistency means I'm not constantly working around framework limitation in different areas. It's the most balanced and complete framework. Reason 5, open source without lock-in. Unlike OpenAI agents, LangChain doesn't lock me into a vendor ecosystem. I can switch LLM providers, change infrastructure, modify deployment patterns without rewriting my entire application. In production, this flexibility matters for cost optimization, redundancy, and avoiding vendor dependency. So, here's something critical, okay? Even though I choose LangChain and LangGraph, just remember this part. I don't use, and you don't have to use, all its abstraction blindly. The problem with over abstraction actually, that high-level frameworks are seductive, of course. They promise to solve everything with minimal code, but here's what happens. First, you lose understanding. of what's actually happening. Second, debugging becomes impossible when things break. Customization hits walls. When you need behavior that frameworks didn't anticipate, code becomes brittle because you don't understand the abstraction you are using. So my approach is strategic abstraction. When I use LangChain LangGraph, I follow these principles. Use abstraction for standard features that don't require customization. State management, checkpointing. Okay, use LangGraph built-in system. Token counting with cost track, and use get OpenAI callback. Basic tool calling, use the frameworks tool wrapper. These are boilerplate features that every application needs. They are well tested, standardized, and not worth re-implementing. Using the framework here makes development faster without sacrificing control. Use vanilla Python for custom logic, complex business rules, write vanilla Python. Custom state transition, explicit Python function, unique agent behaviors, clear vanilla Python classes, data transformation, standard Python, not framework abstractions. This keeps the code clear, understandable, and maintainable. Future developers, including future me, can read the code and understand exactly what's happening without deep framework knowledge. We have journeyed through 6 major AI agent frameworks, analyzed them across 6 critical feature categories. Remember, frameworks are tools, not solutions. The best framework is the one that aligns with your specific needs, your team's expertise, and your project requirements. Use abstraction where they provide value, but never ever hesitate to write vanilla Python where clarity matters more than convenience. Thank you for joining me on this comprehensive benchmark journey. I hope this analysis helps you make informed decision for your next AI project. Until next time, keep building, keep learning, and keep your code clear. Happy coding and goodbye.